Hello everyone, and welcome to this first ever Raku Conference. So I'm really excited to see how it will go. So we have 3 days instead actually of the only single day that was planned originally. So yeah, we have enough talks for 3 days. Well, today is a special day because today we have only 2 talks, but there's a long talk and there's a very long talk, 4 hours and maybe even more. So it's kind of master classes as we used to have on regular conferences. So so it's online now, and just to avoid some noises, all the microphones are muted for all the participants. If you want to talk, please raise hand, but that only makes sense if the talk is live. So if it was a recording, well, yeah, there's no chance to speak. Well, there's yeah. So, but you can use the chat. You can just type, and if the speaker is here, if the talk is recorded, and if the speaker is here, so yeah, you can interact with them. And after the talk, again, if the speaker is here, we can try to have the QA session, but it will be after the talk. If the talk is live, yeah, you can just interact whenever you want, if the speaker allows that. I would like to thank our sponsors. So we have 2 sponsors this time. It's pearlservices.de and Edument. You will see some ads from them today. We have 3 days. So every day we start at the same time. It's 3 o'clock, 3 p.m. UTC. And yeah, so I hope you will enjoy the conference, and I wish you a good weekend and a successful conference. So yeah.
Sockwell, though some of you may know me better by my username code sections. And this talk is entitled 105 C++ algorithms in one line of Raku each. Now, in addition to being a Raku developer, I'm also a lawyer, and I feel the need to say that this talk title should really have a few asterisks by it. The 105 number comes from the algorithms header in C++. This talk will walk through most, but not all of those 105, plus a few bonus ones. So I think the 105 is still about right numerically, but may not be 100% accurate. On C++, as I said, most of these algorithms are drawn from the C++ algorithms header, but some of the bonus ones are not from C++, so there's a slight footnote there. And then on the one-line business, there's a slight footnote in that although all of these can be done in one line of Raku, for the purposes of formatting, I've split some up on the slides. But with all of those footnotes out of the way, I want to start with a basic question. Why am I giving a talk about 105 C++ algorithms in one line of Raku? In a lot of ways, I'm giving this talk because it's a talk that I wish I could have seen when I was first starting to program Raku a few years ago. When I first started learning Raku, there were so many language features I loved, but there were also times when I would reach for a function from the standard library from Rust or some other language I'd programmed in, and not be able to find it in Raku, and conclude that Raku just was missing some functionality that I was used to. To give an example, I really clearly remember this happening with the Rust function filter map. So for those of you who may not know Rust, the filter map function allows you to iterate through a collection and then either filter an item out of the collection or keep it and transform it in some way. And it does that in one pass so that you don't need to iterate through the collection twice. And I searched the Raku documentation for an equivalent function and didn't find one, and concluded, like, oh, well, Rust is really focused on low-level performance. Raku is a higher-level language, so maybe it's okay in Raku to just map over a collection, and then after you've transformed all the elements, filter out the ones you don't want with grep. And like, yeah, you end up iterating over the collection twice, which has some performance cost, but probably not that big a deal if you're not doing something super performance sensitive. And I thought that's just the way it was. And then a little while later, I realized, wait, hang on. It's not that Raku doesn't have a filter map function because it's not worth including that functionality. Raku doesn't have a filter map function because it doesn't need a separate function for that, because we can already do that in Raku with map. All we need to do is use the Raku primitive idea of empty, or a slipped empty list, and combined with map, we can iterate through the collection with map. If we want to keep an item, then we can transform it in some way and with a function. And if we don't want to keep it, we can just return empty, which has the effect of excluding that item from the return value. And as an aside, that it has some interesting sort of type theory implications for Raku's map, in that it is not what a functional programmer would really call map. It's not guaranteed to return a list of the same type, a list of the same length. But that's an aside. The point here is that there was functionality that was entirely built into Raku, but that I didn't know about as a beginning raccoon, because I was looking for a filter map equivalent, and there is no function that is the equivalent of filter map. It is just an emergent item, an emergent piece of functionality that comes naturally from a combination of some really good primitives that Raku has built into it. And there are a tremendous number of features like that in Raku, and I started thinking, maybe if only there were a list of those features, it would be very helpful to me. And ever since then, I've been thinking, like, one day I'm going to give a presentation that collects some of those sort of hidden emergent pieces of functionality. I got started with this presentation by thinking about what I would have wanted when learning Raku, but I also know that I am not at all the only one who could benefit from this. Literally on the day that I was finishing this presentation up, I came across a comment posted to GitHub by someone who's new to Raku, and I have the screenshot here where the only thing I've changed is the user's screen name. And they said that they were new to Raku and liked some things, but were confused because they couldn't find simple statistical functions like mean or standard deviation. Now, I have two thoughts about that. First, it is absolutely true that there is no average or mean function or method built into Raku. Second, it is absolutely true that we don't need an average function built in, because we can compute an average just by taking the sum of a list of numbers and dividing that by the length of the list. And doing that is better than having an average function. It's better because it actually takes fewer characters to write, and it avoids any ambiguity about, is this average as in an arithmetic mean or a geometric mean or a median. What exactly this code is doing is 100% clear in a way that wouldn't be true if we had a dot average function. However, it does lead to this problem where someone searches our docs and says, hey, what's up with this language that says it could be good for math, but they don't even have an average function? So people, every day there are new raccoons who come to the language and think that we're missing features that we're not. And so part of my goal with this presentation is to sort of lay out how some of these common pieces of functionality can be achieved just by combining primitives such as sum and taking the length of an array just by casting it to a number. More specifically, I have two goals for this presentation. First, I want to actually teach the specific patterns that are required for the 105 functions I'll be walking through. I want this talk to be a resource where you will come out of it knowing what Raku primitives to reach for to implement each of these functions. But perhaps even more importantly than that, I hope that this talk can be a way to build intuition for the ways in which Raku primitives can be combined to implement different functions in line and in a single expression in a way that replace or remove the need for some things that might be built-in functions provided by the standard library of some other language. And I think that is actually the more important objective here. As long as a list of 105 algorithms might seem, it isn't everything. And I think the intuition is even more important than the specific details. Before getting started, though, I want to address the question of why C++. I mentioned that I came to Raku from Rust and have really never been a C++ developer. So why am I talking about C++ algorithms instead of ones from Rust or JavaScript or Perl or any other language I could have picked? Well, partly it's because of a few different reasons. C++ has familiar syntax to people who know C family languages. It also has a rich standard library that gives a lot of algorithms to work with and draw on for this talk. But it's also because I'm somewhat riffing on a really excellent talk titled 105 STL Algorithms in Less Than an Hour. And I really recommend that you watch that talk, but I'd actually like to play you an excerpt from it right now.
What we're going to talk about today is the STL algorithms. We're going to start off this talk with a question to you. Who in this room is aware of the fact that it's a good thing to know the STL algorithms? Just raise your hand if you're aware of that. That's pretty much everyone hands rising. That's pretty cool. Second question, who knows them all? Raise your hand. Go on then. That's pretty much that. That's actually no one's hands rising now. That's exactly the purpose of this talk. When you walk out of that room, you will know every single thing that's in the STL algorithms library. To do that, I suggest that we start with a brief chat about why it's important to know them and what to learn in them, and then we dive in the STL algorithms themselves. All right? So there's this thing that's been popularized across the C++ community over the past few years. That's we need to know all the STL algorithms, and we need to know them well, very well. But why? Well, for one thing, they can make our code more expressive. And they do that by raising levels of abstraction, which means that they allow you to express what we want to do as opposed to how we want it executed. And I think that raising the level of abstraction is one of the most efficient ways to write expressive code. And it can be sometimes spectacular. Like if you've seen that talk a couple of years back by Sean Parent, which was called C++ Seasoning, in that talk Sean took a chunk of code that was a bit hard to understand, and he refactored it into a more concise and expressive piece of code just by picking the right STL algorithm.
Now, I am absolutely all for writing concise and expressive code, but I want to push back on part of what he said. He just said that one of the best ways to write expressive code is to raise the level of abstraction. And I disagree, or at least disagree that is nearly always the case. Aaron Hsu has a phrase that, I don't know if he coined it, but it's where I first heard it, transparency over abstraction. And I think that there are many times where software developers reach for abstraction prematurely and use abstraction, and particularly black box abstraction, where the implementation details are hidden away, as a way to hide away details that actually aren't irrelevant, that actually do matter. So, to go back to the average function, yes, that is an abstraction that can be helpful, but if it isn't clear to the caller what that is doing, whether it's taking the mean or the median, then that can be an abstraction that is confusing. Whereas if you have transparent, where we're adding all of the elements and we're dividing by the number of elements, you know exactly what that's doing. That level of transparency is extremely helpful. and I think actually far more expressive than the black box abstraction that just hides that away. I think that expressive code is excellent, but I care not just about expressiveness at the call site, but expressiveness of the entire code project as a whole. So if there is code that reads very cleanly at the call site, but causes a programmer who's debugging it to need to use IDE or editor function where they're constantly jumping to definition to say, oh, well, I see this function, but I don't know what it does, and I need to know what it does. So I'm going to jump to the definition of that function. And then that function calls 5 others, and I need to know what they do. And so I'm going to jump to definition there. That is a time where abstraction has not made the code clearer. It's made the code more confusing and less expressive, and that the code clarity would have been increased by using transparency rather than abstraction. So in a lot of ways, that's sort of the hidden thesis of this talk, is that not only is it fine that Raku doesn't have some of these functions that C++ or other languages might have in a rich standard library, it's actually better that we as raccoons get that functionality by combining primitives, because it gives us a less abstract and more transparent way to achieve that same functionality. We can, in a line of code that is no longer or barely any longer than a long function name, can see exactly what is being done and don't need to have that jump to definition abstraction penalty. So that's something I'd like you to keep an eye out for as we go through these examples. Keep an eye out for places where the functionality is where the C++ name might not be clear, where you might have some abstraction that, yes, hides away details, but that just from the name, without checking the documentation, you wouldn't necessarily know what is going on. And take a look at the corresponding Raku code that we'll be walking through and say, could I know what that code is doing in a way that I wouldn't with the more abstract version? And I hope that you'll end up agreeing with me that there are many places where that abstraction is over abstraction, and where the transparency provided by the Raku expression results in code being clearer. The first function I want to start with is actually one of those bonus ones I mentioned that is not from the C++ algorithm header, but it's one that is probably familiar to any of the functional programmers in the audience, and it's one that will be very helpful to us in implementing some of the other C++ algorithms. So I thought it would be an excellent place to start, and that is ziptail. That is a function that takes a list and returns a new list that is comprised of each element in the original list paired with the following item in the original list. So if you had the list 1, 2, 3, ziptail would give you back a list containing the pairs 1, 2 and the pair 2, 3. And by pair, I don't mean the Raku data structure pair. I mean a 2-element sublist. So implementing this in Raku is very easy. The most straightforward way would be to just take a list and zip it together with a version of that list containing items starting from index 1 all the way to the end of the list. I actually prefer a slight variant on that instead of using array indexing to index into the second list, just says what we want from the list is, for the right-hand side of our zip, is the original list skipping the first element. So here, a.skip. The only problem with this implementation is that we're repeating the reference to our array A, which is not a problem for expressiveness there, but if we were using a longer name, then repeating that longer name on both sides of the zip expression would be a little bit cumbersome. So My actually preferred spelling for ziptail is this one here, where we are using an anonymous method to say we want to start with a list and then take that list and zip it together with that list, having skipped the first element of the list. To me, that reads very, very expressively and says exactly what we want to do with ziptail. There is a different spelling for ziptail, which uses the .rotor method. So you can say we want to take a list and rotate it into batches with 2 elements each and a -1 element gap between each batch. A -1 element gap, of course, means a 1 element overlap. And that gets you exactly the same thing. I don't like that spelling quite as much because it's not as expressive in terms, it doesn't encode the idea that we're zipping together anything, and it is also slightly longer, and I really like the anonymous method syntax, and it's something that will come in handy in several of our other implementations that I'll be going through in this talk. So I wanted to start with that and go ahead and introduce that, and I'll be using the anonymous method ziptail implementation as we go forward, but I do want to mention the rotor one in case you come across that spelling. Similarly, the next function I want to talk about is also a building block that is not from the C++ algorithm header, but that we'll use in implementing functions from it, and that is just useful in its own right. And that is a binary filter. That is, if you have a list A and you want to filter items in or out of that based on some binary predicates that you have in list B, then binary filter is the way to do that. So let me walk through the implementation and then also an example, since that is a little bit abstract to describe. So the way we implement this is very simple. We just use the hyperoperator to AND together each element of the binary predicate list with the list of interest. So if the list that we are interested in, it contains foo, bar, baz, and buzz, and we have a binary predicate list of true, false, false, and true, then we can apply that and AND them together with the hyperoperator, apply our binary predicate, and get foo, false, false, buzz. Note that if we don't want to get the falses in there, we can, of course, grep over the resulting list and exclude anything that is false and ended up just with foo and buzz. If you are confident that your list does not have any falsy values, then you could simplify this grep and just look to keep truthy values. Here I'm only excluding things that are literally false rather than falsy, but which is the more general approach. But if you were confident of that your list A did not have empty strings or zeros or other falsy values, then you could simplify that grep a bit. Okay, now let's dive into some functions that actually are in the C++ algorithms header. We'll start off very easy with functions that from the algorithms header that do appear in Raku, but that have a different name, and thus you might not find in the Raku documentation if you are searching for them under their C++ name. So, for example, in C++ you can shuffle a vector, an iterator, and in Raku you can pick all of the elements from a list or an array, which provides equivalent functionality. You can, of course, pick a smaller number and get a smaller number of random output, but if you want the entire list in random order, you can pick everything. And then equal is perhaps even more directly equivalent. We have equiv or a few other equality operators, but equiv is the most direct to C++ is equal, we have the much more concise comparison operator, which is the equivalent of C++'s lexicographical compare. I'm not sure if comp is the right way to pronounce that. That's how I say it in my head anyway. Next, and still very firmly in the easy camp, we have a group of C++ algorithms that are the equivalent to Raku's junctions. All of is equivalent to our all junction, any of equivalent to our any, and none of our none. Junctions in Raku, of course, have a variety of superpowers and will have an increasingly large variety of superpowers as auto-threading continues to be further developed according to the specification. But even in their most basic level, they can at least serve as equivalents to all of, any of, and none of from languages like C++. A few other easy aliases that I don't have a whole lot to say about. Finding an element in C++ is like looking for the first element in Raku. And of course, with our first, you can get either that element as a pair of its position in a list, or just as the value, if that's what you want, or as a two-element list of the key and the value with the PV or KV named argument, respectively. Our equivalent of C++'s min element is min. Our equivalent to max element is max. And our equivalent to min max element is min max. And one that is you get no points at all for guessing. Our equivalent to their unique is unique, which may be uniquely the only time we have exactly the same word that C++ uses. Now we're getting into some of the functions from C++'s algorithm header that, while we're still essentially in alias territory and haven't gotten into the heart of what I want to talk about, we're at least getting to a point where I have something to say about these algorithms. So we handle both sort and stable sort with our sort, which it defaults to being stable. So that is one area where we don't have a direct equivalent to an unstable sort. There are ways you could do that, but this is more of the high-level nature of Raku showing through a bit. It is typically not the case in Raku that we're concerned about performance at a low enough level that using an unstable sort is helpful. So which means we're able to sort of kill two birds with one stone and use sort without having to worry about its stability. Now this next one is especially interesting because we're also able to kill two birds with one stone by handling reduce and accumulate with just our reduce. I think accumulate is an especially poorly named C++ algorithm in some ways. It is essentially just reduce, but with a default plus operator, but that can be replaced. So it basically is just reduce. And then C++'s reduce is one that has some constraints on it to guarantee that it can be parallelized. That's something that we handle, again, with a bit less abstraction by using reduce sequentially, or reduce with hyper, or reduce with race, depending on what type of parallelism you're interested in introducing. And then we don't necessarily have the same type system guarantees that the operation can be safely parallelized, but we can attempt to parallelize it and successfully parallelize anything that we can using reduce with race if output order doesn't matter, or with hyper if the output order does matter. Similarly, we can handle partial C++'s partial sum or inclusive scan with produce, or in the case of inclusive scan, produce paired with the appropriate parallel algorithm and a function that can be appropriately parallelized. And again, just like accumulate is oddly named in C++ by sort of encoding into the name what operation is there by default, but that can be overloaded. Partial sum encodes the idea that sum is the default operation, but produce doesn't have that encoded into the name, but you can easily supply the plus operator if you would like to that to be the default operation. One thing I also have to say about reduce and produce is that they are obviously extremely similar algorithms. Reduce takes a list and iterates through it, a list or an array or other iterable collection, and iterates through it and applies a function to build up an accumulated result, and then returns that final single value. And produce does exactly the same thing, but it returns a list of all of the intermediate values being produced along the way. In many functional languages, these are known as reduce and scan, or sometimes fold and scan. And what I dislike about those names, even though admittedly fold and scan are shorter than reduce and produce, is that those names don't have any indication that the algorithms are so similar. Reduce and produce just sound similar, and that's something that I love about Raku, is that things that sound the same typically are the same. And other than APL, which uses a backward slash for produce and a forward slash for reduce, or maybe I have that backwards, I don't know of another language that so closely indicates the similarity between these two algorithms. So that's something that I've always really liked about Raku. Moving on, C++'s transform is the same as our map. Map is the normal term for that. I'm not sure why C++ went with transform. It's much longer and not nearly as commonly used. And then C++'s for each is we can achieve the same thing with our for, not a function, but a keyword. One thing that I should note about for is that, of course, Raku's for is not a traditional for with from a C family language that takes three-part iterator and everything afterwards, where you're doing I++, etc. For is just directly iterating over a loop, iterating over an iterable collection in a loop, and also notably, one of the ways that for each is used in C++ is to have an expression rather than a statement. But of course, any Raku statement can be turned into an expression with do notation. So do for can achieve the same thing that you might use a for each for, or just by wrapping it in parentheses, which achieves the same effect. So either for or for in parentheses or do for will give you a very similar output to for each from C++. Next, we come to an area where we're still dealing with aliases, but no longer aliases to Raku words, but to Raku symbols, specifically Unicode symbols that we use for set operations, the actual mathematical symbols that are used for those. So instead of set intersection, we have the mathematical symbol for set intersection. Instead of set union, the mathematical symbol for set union. Instead of includes, we use the element operator in whichever direction you would like to, which allows more expressive code there. And then instead of the absolutely longest item in STL, set symmetric difference, we use the set symmetric difference operator. Now, I know some people would say that as concise as these operators are, that we should use more verbose and thus more descriptive names like set symmetric difference. But I would argue that there is the set of people who really know what set symmetric difference means, but who don't know that symbol is very small. There are plenty of people who don't know the mathematical symbols for set operations, but I think most of those people, most of us, I would say, who don't really work with set operations, and I put myself in that camp, don't really know what these terms mean either. If you're somebody who doesn't know set operations well enough to be familiar with mathematical notation for them, there's a good chance that you don't really know them. So I think that having these concise symbols in Raku not only improves the concision and readability of Raku code to those of us who are familiar with the mathematical notation, but also avoids sort of abstracting away something with a name that is just descriptive enough to be confusing. On the other hand, I think that one area where Raku is a bit confusing and its embrace of the mathematical notation is a bit confusing is with set difference, which is the one area where I will always default to the Unicode, to the ASCII representation rather than the Unicode. I know that this is a distinct Unicode character from a backslash, and I know that it is the mathematical symbol for set difference, but unless I am very clearly operating in a set context, I cannot imagine that I would distinguish that from the corresponding character for a backslash, and I cannot imagine that it would be anything other than confusing. So that is the one area where I will use the ASCII character equivalent, but everywhere else I strongly prefer the Unicode and think that it results in Raku code being much more readable for not only for set operations, but especially for set operations. So I'm glad that we have these equivalents to the set operations from the C++ algorithm header. All right, so now we're on to the last batch of algorithms from the C++ algorithm header that have direct sort of alias type equivalents in Raku. These are not ones that have similarly named functions, but ones that have symbols, not Unicode symbols necessarily, like we saw with the set operators, but symbols or other functions that provide a similar functionality. So to produce the same output as C++'s fill algorithm, you can use the list replication XX operator. It is more powerful and has more advanced use cases, but a very trivial use case of it is to duplicate the functionality of fill. So for example, if you wanted to fill a list with 10 copies of the integer 42, you would do 42xx10, which duplicates 42 10 times. Again, you can do more advanced functionality with that same operator, which I'm not getting into at the moment, but that is a trivial use for it. Similarly, if you want to duplicate C++'s generate, you can use the sequence operator in Raku, which again, it has a more advanced use case, but a very simple way to use it is to give it a function that it will use to generate each element of a sequence, just as C++'s generate algorithm does. Next, C++ has the iota algorithm, which takes a terminal value and generates a iterator up to that terminal value, 0, 1, 2, 3, 4, all the way up to but not including the terminal value. That is the exact functionality provided by the up-caret range prefix range operator in Raku. So up-caret 10 gives you 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but not 10. And just like iota, as I mentioned with the list replication operator and the sequence operator, the range operators, and it's really a family of operators, provides more advanced functionality in Raku, the ability to specify a beginning value rather than defaulting to 0, the ability to exclude or include beginning and ending elements of the range. But for just the basic iota functionality, all you need is the prefix up-caret. And then on a slightly different note, but I want to mention it while we're still in this last of the freebies slide, C++ has transform reduce, but the reduce functionality in Raku is actually powerful enough to provide that same functionality with inline functions and the ability to transform your output before adding it into your accumulator. That may involve using one of Raku's sort of secret weapons of a state variable, or it may not. But regardless, transform reduce is sort of a subset of what we can handle just with reduce. And I wanted to mention that here since it is different enough to be worth calling out. All right, we're now to the point where we're actually implementing functionality ourselves rather than just relying on something being called something else in Raku than it is in C++. However, we're not to the hard stuff quite yet. So if we want to have the Raku equivalent of C++'s remove, we can just grep over a list of elements and filter out any that do not pass our predicate. So just invert the predicate that we're testing against. Similarly, if we want to count how many elements pass the predicate test, then we just grep over the list, get the passing elements, and then convert that to a number, which just gives us the count, exactly what we were looking for. Next, if we want to get a copy with certain elements replaced, map is our friend there as well. We just use the ternary operator, map over. If it passes our test, we transition to whatever new element we want to replace it with. And if it fails the test, we just pass it on through as is. And that has the effect of giving us a copy with certain elements replaced. And then find end, lower bound, and upper bound can all be implemented with the Raku function first. And depending on whether we want the lower bound or upper bound, we would need to pass the end named parameter, but that'll either find the first or the last element that passes that test. And then last and most difficult of this sort of easy batch is partition. And like with sort, Raku is going to have everything be stable by default. So we don't have to distinguish between partition and stable partition. But to implement partition, what we do is we use the classify method and pass it whatever predicate we want and then cast that to a number. So let me walk through what that does in a little more detail, because like I said, this is the first sort of more intermediate function that we're implementing. Classify will give us a hash of a hash as our output, and the keys of that will be whatever we return from our function. So here, our predicate function, which is going to return true or false, but then we cast that to a number, so that will return 0 or 1. And we'll get a hash whose keys are 0 and 1. And what will the values be? Well, the way classify works is the values will be all of the items from the original list that we were iterating over sorted into the key that corresponds to the return value for that item. So 1 will have all of the items where our predicate returned something that was cast to 1, that is all of the items where our predicate returned true, and 0 will have all of the items where our predicate returned false. So that has the effect of classifying our items, but we wanted them to be returned in a particular order to match the API of C++'s partition. So the problem that we would have with Raku is that not only are our hashes not guaranteed to be in insertion order, they are actually guaranteed to not be in any stable order at all to prevent subtle bugs from showing up later. So we can't count on the first key value pair being the items that passed our predicate and the second being the ones that failed, or vice versa. That means that to get a particular order, we need to actually index into the keys that we want. Fortunately, a multi-slice of all of the items with a key of 1 followed by all the items with a key of 0 makes that very easy and gets us a single list of a stably partitioned set of the elements that we started with. And now we have a series of functions dealing with permutations, which are definitely on the easier side of the functions we'll be implementing, but slightly non-intuitive, at least at first. And the part that I think is least intuitive about them is the implementation of is-permutation, which is actually, in Raku, all it takes is testing for set equality. Why is that enough to fully implement the C++ is-permutation? Well, what it means for one list to be a permutation of another is that the two lists are the same but with different order. And what it means for two sets to be the same is to be equal is that they have the same members. So anything that is a permutation will pass set equality for a corresponding list. We can also implement next permutation a bit more intuitively. We just use the permutations method and look for the first item on it. And previous permutations, correspondingly, we take the last item in permutations. Of course, a slight difference in the API here is next permutation you could call again and again to iterate through permutations, whereas with our permutations method in Raku, you would get a collection and you would actually need to iterate through it yourself. But that has the advantage of where you are in the collection of permutations, which has some ergonomic advantages and disadvantages compared to being able to just call next with next permutation. But on the whole, I think is a good trade-off from expressiveness and ease of use perspective. All right, now we're getting into some that I find especially exciting to tell you about, both because they show off some of the features that make Raku so expressive and such a good match for implementing these sorts of functions, and because they demonstrate some of the difficulties that I think C++'s high level of abstraction here create. We're getting into several areas where the C++ algorithm function has a name that is expressive in terms of its default operation, but that does not really capture the full power of the function in question. And I think that lowering the level of abstraction the way Raku does really helps clarify some of these examples, but I'll point that out as we go through this slide. To do that, we're going to make use of the zip tail, which I showed you before, which just as a quick refresher is the implementation I have here uses an anonymous method to zip a list together with a copy of itself where the first element has been skipped. Using that function, we can implement isSorted just by zipping together a list with ziptail and then applying with zip as a meta operator the less than operator, which will get us a list not of pairs of items zipped together, but of just booleans that tell us whether or not each item is less than the item that follows it. And of course, if every item is less than the item that follows it, then our list is correctly sorted in ascending order. So if all of those values are true, and we coerce that to a boolean, and that returns true, then our list is sorted. If it returns false because not all of those were true, then our list was not sorted. And this allows us to implement isSorted. But note that if we want to test for something other than sorting, then because we have a transparent implementation here, you can see exactly where we're doing that comparison, and you can replace the less than operator with any operator or indeed any binary function that you'd like, and get that transparently without having to think about an operator overload or something that you can pass to isSorted that causes it to behave differently. All right, so we can do something very similar with isSorted until, except instead of directly passing our operator to zip as a meta operator, we will just do our normal zip tail and get pairs and then map over those pairs and test whether each item is sorted. And if it is, proceed on to the next. And if they're all sorted, then just sum up the count and say that it's sorted until the very end of the list. But if we ever get to a point where an item is not less than the following item that it's been paired up with, we need to bail out early, which Raku lets us do. Again, many map implementations would not let us bail out early in that way because map in a pure functional language with a strong type system, map would be guaranteed to return a list of the same length, but we have a bit more flexibility than that in Raku, and we're allowed to return a shorter list if we want to using last. So that's exactly what we do here. If our test ever fails, then the OR proceeds on to its second half, and last bails out early. Our map stops short, and then when we sum up the number of trues, we get a number that tells us exactly what index we reached with all of our items being sorted. All right, and next, again, adjacent difference is one of those sort of poorly or at least incompletely named C++ algorithms. What it does is, in its default implementation, it tells you it's well named in its default implementation. It tells you what the difference between each adjacent pair of items in the list is. That is, what is the first item minus the second item. And that's exactly what this implementation does. Ziptail applying minus as our binary operator gives us the adjacent difference. However, the C++ adjacent difference can be used much more flexibly than that. It can be passed to any other binary operator, and similarly, our ziptail here can of course be passed to any other binary operator. But unlike the C++ algorithm, which has the idea of its default operator encoded into a name that is confusing if you're passing it some other operation, here we have just a transparent description. And I don't point this out every time, but note here that we have something that is in fact shorter than the function it is replacing. So not only is it clearer, not only is it more transparent, it's actually more concise. So I think this is a really clear win for Raku. That the brevity point is not true for adjacent find, which is our next algorithm, but everything else that I just said is. We once again have a C++ algorithm that is named well for its default case, but is named confusingly for non-default usage. What adjacent find does by default is test elements and find the first repeated pair. So, if you have a list 1, 2, 3, 3, 4, it would say, oh, 3 is the first time that I found something that is the same as an adjacent element. And that's exactly what our implementation here does. We do our, by now, familiar zip tail, and then look for the first pair where the adjacent elements are double equal to each other. We could use a different predicate if we were interested in a different sort of equality. And then that will give us that pair as the first, the return value from the first function will be the first pair that satisfies that predicate. But adjacent find is just interested in the actual first value. So to match that API, we then index into the pair and take its first item from the pair. And again, like adjacent find is clear in the default case, we are also clear we have that equals inside our reduce meta operator that makes it very explicit about what we're doing here. But we go a little bit further than that, because if we want to put a different operator in there, any binary predicate would work just fine, a different sort of equality or a custom function. It remains clear what we're doing, whereas in C++, you have sort of the cognitive dissonance, cognitive overhead of saying, well, adjacent find, except I'm overloading something so it's not actually engaged in finding anything. Once again, I hope this is illustrating the value of transparency. All right, for this next batch of functions, we're going to not only need our now good friend ziptail, but also the other building block helper function I introduced earlier, binary filter. So just a very quick refresher on that. That function is a function over two arrays or lists A and B, and A contains elements of interest, and B contains a binary list, a list of booleans or boolean-like elements, and then we use B as a filter on A and remove all of the elements that are not that correspond to a falsy value in B. We remove those from A, and every element that is at an index that has a truthy value in B, we keep that in A. Okay, so how can we use a binary filter to implement the C++ algorithm mismatch? Which, by the way, I know I've mentioned several poorly named C++ algorithms, but I have heard mismatch described as the single worst name in the C++ algorithm header. So what does mismatch even do? Well, mismatch, its default implementation anyway, takes two arrays and tells us, it returns to us the first element that is not the same in the two arrays, the first time that there is a mismatch between the elements at the same index in those arrays. So how would we implement that? Well, we do our familiar zip, but instead of zipping with a list with its own tail, we zip these two different lists together. And then on our zip meta operator, we apply that to the not equal to, which note what Raku is doing here. We have the triple equal to operator modified by the meta operator that negates binary operators, modified by the zip meta operator. So we have a meta operator, which is really Raku kind of showing off here. But in any event, that zipping those two lists together gets us a list of booleans, where we have false if the two arrays are equal, and true if the elements at the same index of the two arrays are equal. True if they are not equal, because of that negation there. So we have a list of booleans, and a list of booleans is exactly what we need for our binary filter. So we do that binary filter on A, which gives us a list that consists either of false or of the element that was not equal. And then we look for the first element in that array, because that will be the first mismatch, and that's our result. The first element that is not false. So why is this such a poorly named function in C++? It really does give us the first mismatch. Well, because that's just the default behavior. And looking for the first mismatch in two arrays is really not that useful. But mismatch is, in C++, a very useful algorithm, because you can overload the not equals operator and find all sorts of, have many more useful predicates to compare to arrays. But that is totally obscured by the abstraction and the black box of the name. Without checking the API docs, you don't necessarily know that from the name. Whereas looking at this function that we've written out here, you see exactly what it's doing and know just by looking at it that you can put in a different operator instead of this equality operator or this not equality operator, and find whatever it is you're looking for. So once again, this transparency, I hope you're starting to see the value of it. All right. Let's move on to the C++ algorithm is partitioned. Before diving into an implementation, what does is partitioned do? Well, a list is partitioned if it can be divided into a front half and a back half, and the front half should have everything pass a predicate, and the back half should have everything fail a predicate. So it's kind of like being sorted, but less strict. Let me just mention an example. So if you wanted to say, is a list partitioned on the predicate less than 5, then that would mean that the front portion of the list has items that are less than 5, and the back half, again, it shouldn't be half. We don't know how much, but the back portion of the list has elements that are not less than 5. So it's like sorting, but you don't know that everything is in ascending order. You just know that there's a portion of the list that passes and a portion that fails, and it doesn't flip-flop between the two. So let's take a look at how we implement that in Raku. So first we use our very good friend ziptail, and we have a list of pairs, and then we map over that list, and we say, is there does the first element pass the predicate, and does the second element pass the predicate, fail the predicate? And if that is true, then that means that we're at a point where there is a sort of break, and that is our partition point. If that is less than or equal to 1, that means there should be 0 or 1 partition points in a correctly partitioned list, then is partitioned is true. If that is 2 or more, then we know that there are multiple partition points, but that you can't have multiple partition points in a correctly partitioned array. So then that would return false. And that is exactly what isPartition does in C++. Note that this one is a bit verbose. I mean, I don't insist that these be absolutely shorter or anything than the C++ equivalent, but this one is getting a little long. So I don't tend to work with partition lists that often. If I did, this was the sort of length where I might start saving this in a helper function. But even so, it's nice to be able to see it just in one line and know what it is we're dealing with. C++ also offers the isPartitioned until, and that implementation in Raku is pretty much a carbon copy of isPartitioned, except instead of checking to see whether we have just a single partition point, we actually use our friend the binary filter, and then find the first place where that is, and that gives us the how long the partition goes, and we get that first item. Partition point is nearly the same, except instead of returning that item, we're going to return the index, which gives us the a different access to the same information, essentially. And so those are all of C++'s partition-related algorithms. Okay, with this next slide, we're going to finish off the core C++ algorithms that we'll be covering. And the first function I want to do to talk about to do that is one that I'm very happy with the Raku implementation of, and that's inner product. The reason I like the Raku implementation of inner product so much is because I'm not really sure why. Maybe because my math education stopped with the second semester of calculus in undergrad, but I can never keep the order of operation straight for inner product. But I can keep it straight just fine with the Raku implementation, which is zip two lists together, multiplying each element, and then sum each of those multiplication results. So it's multiply and then add, and that is clear, just transparently obvious from the implementation. No need to check the documentation or type into a DuckDuckGo search what inner product is. And of course, if you want to apply different operations, it's exactly clear where you plug them in. Don't have to check the order for function overloads or anything like that. Transparency helps us out. The next operation from the algorithms header is exclusive scan, which is pretty much trivially implementable as a produce operation here, given the plus function, which is the default for exclusive scan, but we can pass it anything we want. This shows the power of Raku's slip operator. In many languages, you need an overloaded version of a produce or a reduce to be able to pass in a starting value or a default value. But with Raku, of course, we can just create a new list that consists of whatever starting value we want, with a slipped version of our starting list, which just easily appends that first item to the beginning of our list. Note that we do need to manually provide the correct identity value, which is, so if we're adding, as we are here, 0 is an identity value, but 0 is not an identity value for multiplication. The product of 0 and anything is 0, so we would need to supply 1 as the identity value there. so there is that limitation to our implementation, but other than that, it is exclusive scan. The last two things that we're pulling from C++ implementations are fairly trivial, but I just want to mention them here for completeness. Transform reduce, which is just map reduce, and transform inclusive scan, which is just map followed by produce. Once again, C++ feels the need to break these out into separate operations to have to give the programmer fine-grained control over parallelism, but we implement the same thing by having the option to apply race or hyper to get parallel implementations of MapReduce or MapProduce. Now, if any of you have been even vaguely counting along, you might have been surprised to hear me say that we are to the end of the core algorithms from C++'s 105 algorithms in the algorithm header, because I'm not sure of the exact count, but we definitely haven't implemented 105. But I said we're to the end of the core because a lot of the actual numbers in the C++ algorithm header comes from what the video that I'm riffing off of described as secret runes, which are modifiers like copy, not, if, and in that are applied to sort of pad out the number of algorithms. So you may have something that sorts or in place versus a sort copy that returns a new copy. And the thing about those in the C++ algorithm header is, although they are relatively consistent in terms of providing these sort of alternate versions of their algorithms, they are consistent only by convention. Someone had to manually implement a in-place version of an algorithm plus a copy version of an algorithm, and they, while pretty consistent to do so where it makes sense, they don't always, and so you have to look that up, and you don't get those for free. If you want to implement your own algorithms, you need to decide whether you're going to implement an in-place version, a copy version, or a both version. Raku takes a slightly different approach, and I think a better one here, in the same sort of compositional way we've been talking about. We have pretty much everything I have shown you so far has been a copy version, but we can compose that to do it in place with the dot equals meta operator. So, if we want to have a sort, instead of a dot sort, we can do a dot equals sort, and that will sort in place. We'll assign the new copy back to the original variable. Whether or not that counts as in place is a little bit debatable if you're looking at it from a pure memory efficiency point of view, but it's effectively in place from a variable assignment point of view. Similarly, as I've already mentioned, we have not only as a negation operator, but also as a binary meta operator. So anything that we can do as an operator, we can do a not version as a negated relational operator. And that gives us all of the not versions essentially for free. And if we have an if expression or a do if expression, or if you want to do something or something else with an else, the ternary also works. Ternary operator also works. And, in many C family languages, if can only be a statement, but by either using do if or just wrapping the if expression in parentheses, we can have that be an expression in Raku. So that allows us to just change the transparent implementation of any of the functions I showed before to have that conditional logic embedded directly in them. And similarly, because we can implement the in version, which limits the application of a function to a certain number of times by using last. A last always, unlike many languages that don't allow for short-circuiting, Raku is very free about allowing short-circuiting with last. And we have the concept of anonymous state variables. So, if you're mapping through a list, then ++ $sign will always give you the current index that you're at. And if you want to just map through the first 10, you can just bail out with last whenever you get to index 10. And similarly with any other iteration construct in the language. So that gives us all of these sort of secret runes, as they're called in C++. It gives us all of those for free. So and this is part of the payoff from having this sort of more transparent approach to our function implementations, because they are not black boxes. There's not that same abstraction barrier. We're free to stick an if or a not or a last right there in the inline implementation, and we are not dependent on a library author to have implemented that version of the function for us. We can just compose it ourselves right there inline transparently. So with that, we have finished all of the algorithms from the C++ algorithm header that I wanted to cover. But as I mentioned, there were a few that didn't seem quite right to include that dealt with heaps, or a few that dealt with some low-level issues. So I do want to just make sure that I'm still getting to about the same number, and include a few sort of bonus ones from outside the algorithm header. And some from outside of C++, but that are good to know and show off some features of Raku that are helpful when thinking through this type of problem. The first is one that we've actually already seen you can do with the reverse method, but I also want you to see that you can combine the reduce meta operator and the reverse meta operator and the comma operator to achieve the same effect. You can just reverse an array with that, and I'm mentioning that in part because it's concise and handy and a nice idiom to know, and in part because we haven't talked about either the reverse operator or much about the reduce meta operator, both of which are good tools to have in your tool belt. I also want to show an implementation of all equal, which is a very handy test to see whether all of, just like it says, all of the elements in a list are equal to each other. And I'm mentioning this in part because it shows off the fact that operators, including the equality operator in Raku, can have what is called list associativity. Normally reduce, if it puts an operator between each element in an array, it wouldn't be able to tell you whether they're all equal, just whether equal returns true when shoved in between each element, which is not necessarily the same thing. But list associativity allows all equal to return true if and only if all of the elements in the list are in fact the same, which is something that very few other languages can implement quite as easily. So that's something I encourage you to dig into if you're interested in that sort of thing. Next, I want to show a couple of string operations. First, just to not forget the very good Unicode and regex support that that Raku has. So, it's pretty trivial to test whether a string is composed entirely of uppercase characters. Just does the beginning to the end consist of one or more uppercase characters and nothing else? And then to make that a Boolean test, cast it to a Boolean. And I could give you a whole page of things you could do with regex that would correspond to methods or functions that might be in another language. But the basic lesson here is anytime you have something, some sort of string operation, and you don't see a method for it in Raku, think for a second, is this something I could do with a pretty trivial regex? Next, I want to mention splitting a string at a particular index. In this example, we're splitting at 3. Note that although strings are not character arrays in Raku, they are easy to turn into a list of characters with comb, and then you can rotor or zip or do whatever you want, operate on them as a list, and then join them back into a string. So that string to list, do something with the list, back to string path is one that is a pattern that you should be aware of, and one that has many more applications than just split at. Here, the rotor implementation is saying, I want to turn this into a two-element list. The first should have 3 items in it, and the second should have everything other than 3. But you can obviously have the full power of Raku to list manipulation to deal with that list once you get the list of characters. And finally, for this slide, I want to mention the power of the sequence operator. The example here is take until, but the point that I'm making here is that we typically think of the sequence operator operating over a list of items that it is generating itself. But note that if you already have a list, you can also use the sequence operator with that existing list. So here the list L could already have certain items in it, and the predicate would still apply. So, if you want to say take until greater than 5, or take until is prime, or whatever, you can apply that not only to a sequence that you're generating on the fly, but also to an already existing sequence, and use that to filter or otherwise manipulate the existing list. So that's another pattern to be aware of. And that is really all the algorithms I wanted to talk about. There are plenty more I could discuss, but in the interest of leaving at least a few minutes for questions, and because I think that's more than enough for one day, I'm going to stop with that, except to return one last time to the GitHub comment that I mentioned at the beginning of today's talk. It mentioned that there were a lot of algorithms missing from the Raku standard library, including standard deviation. And I certainly would be open to including something as complicated as standard deviation in the standard library. It is probably a bit much to define inline. But I also think that it is really worth celebrating how easy Raku makes it to define something like that inline in a expressive way. So here's how a mathematician would write the standard deviation formula, and here's how we'd write the same thing in Raku. Standard deviation is equal to the square root of 1 over the number of elements in an array times the sum of all of the elements in that array modified by taking each element in the array and subtracting the average of the elements in that array, all squared. And to me, that reads pretty well. I look forward to your questions. Thanks so much.
Comma's code analysis and refactoring features help us quickly and easily tidy up our code. For example, here an opportunity was missed to use the with construction instead of if.defined. We can easily change that. Here there's a variable that's completely unused. Let's delete it. This variable name is pretty poor. Thankfully, it's easy to rename it and have all of the usages updated for us.
All right. Well, thank you for sticking around for this presentation. I would love to have questions from anyone. I answered a few in the chat, but I'm happy to take any either by chat or if people would like to raise their hand to be unmuted. Well, I'll be best positioned to answer questions about my talk, but I'm certainly happy to have general questions as well. Let's see, Rob, it looks like you have your hand up. Andrew, are you unmuting people with questions or am I doing that? Okay, Rob, go ahead.
Well, I'm not very advanced on Raku yet, and I find that star, the asterisk, confusing in some of your later presentation items. Like your exclusive scan in the last bracket of that, you have a star -1, and the star seems to come up as a few different things in Raku, and I'm not really finding what it represents there.
Sure. So the star has two uses two categories of uses in Raku. It is either a whatever or part of a whatever code expression. If it is a whatever, then it is being used to in some way that is sort of defined by the function that it is being passed as an argument to. But here in an exclusive scan, the way that is being used is as a whatever code. So it's star -1, which evaluates to the expression of a whatever code, which is sort of whatever -1. There in the indexing context, the whatever code expression is called with the length of the array. So basically what that is saying is the length of the array -1, that is the last element of the array. And that's a pretty common idiom for any array indexing in Raku will have whatever as an alias to the list length allows for indexing from the back of an array. Many languages will actually just let you do, -1 to index to the element right before the end of the array, or -5 or whatever. But with Raku, they decided that it would be clearer to literally subtract from the length, but have whatever be a convenient alias for that length, rather than having supporting negative indices. There's a question in the chat. One property of the STL is that algorithms have specific big O complexity. What approach do you use to determine complexity of Raku one-liners? That is a good point, that these algorithms are, because there aren't like API docs to look up, you can't necessarily say what the algorithmic complexity is by like consulting documentation. The goal with having things be more transparent is because you can see the actual implementation, you can reason about the big O complexity. Of course, that requires knowing the big O complexity of sort of primitive operations built up into Raku. So if you know, oh, I'm iterating through this loop once with a map, you have to know that that is O of n complexity because you are iterating through the loop. But yeah, the idea is that you can look at them and reason about the algorithmic complexity by knowing things about the algorithmic complexity of the components that you are composing. Did that answer the question? All right, well, thank you, everyone. If there aren't any more questions, I guess we can go ahead and stop now and have just a couple minutes before the next talk. There was a last question. Can you talk about iterators more? Yeah, there's that link, and iterators as a C++ concept, I am certainly not an expert on, but they're a way of sort of iterating through iterable objects in terms of iterating on, in terms of iterators as a more general concept. I mentioned them as a Raku term just to refer to anything that can be iterated over. So a list, an array, anything that you can sort of hand to a for loop or a map to iterate over. Yeah, that's a good, from the chat, iterators are a superset of pointers in C++. Andrew Stepanov would probably, or Alexander Stepanov would probably call them coordinates if he redid the STL. I think that's a good way to put it. They are the very layman's, my very layman's understanding of C++ iterators is that they are basically a type of pointer that points to where you are in an iterable collection. But they are used for a lot of areas where we would use a range or an array or a list. C++ is getting ranges, which will replace many of the, or will be another alternative for many of the ways that places they currently use iterators, if I understand correctly. Again, I'm not a C++ expert. All right, thanks everyone. Andrew, back to you.
Yeah, so that was really great. I also enjoyed that. And actually, if you missed something, definitely you can watch it again on YouTube. And there will be the replay of this talk at the end of the third day of the conference. So just for the test to see how it works if we just play the same talk twice. But now, I'm passing the microphone and camera to Vadim Belman. He will talk about how to learn Raku from inside out, and I'm looking at the list of the items there. It's really interesting stuff. How variables are implemented, why everything is an object, argument passing MOP, Meta Object Protocol compile, interpret, Raku compile your own compiler. So it will be, well, officially it's 4-hour talk or masterclass or whatever, but it can be longer or shorter, as basically, yeah, Vadim has a lot of material to share. So I will say thank you for being here. The conference day will end immediately after Vadim finishes his talk, and tomorrow we have day 2. It will begin at 3 o'clock UTC. So yeah, enjoy your talk, and I will pass this to Vadim.
Okay, can you give me screen sharing, please? Andrew.
But everything is good, so we can hear you. So yeah, just go on.
Yes, but I need screen sharing.
Yeah, sure.
And
yeah,
it's disabled.
Try it again.
Good. Okay. I wonder if the screen is now visible.
Not yet.
Could anybody confirm? Yep. Okay, so it's
Yeah, but
my assistant.
We don't see your
Please.
screen, right? Yeah.
Sorry?
We don't see your shared screen yet.
You don't? And share.
Yeah, now it is. Great,
Good.
thank you.
Okay, thank you too. Just trying to find out where is the chat window now. Okay, now I can see the chat as well. So, once again, you already know my name, Vadim. And the thing I'm gonna tell you about is actually not Raku syntax. Even though this class is for beginners, I'm not gonna tell you things like how to say hello world or how to write my $var a SIG42. No way. No things like this. I'm gonna try to tell you about the basic fundamental blocks of Raku and its implementation, Rakudo. At some points, I would be also referring to Perl, maybe, it depends. I'll try to tell things in a way that you wouldn't actually need to know Raku in deep. And actually, if you know just Perl, that's going to be fine too. Because basically, the syntax I'm going to use for examples is very basic syntax, pretty much understandable, and should be no problem to see the idea behind the code. Also, the presentation, which is I'm sharing currently, it's also more like a plan for myself, just not to forget the order to tell things. There will be some illustrations, but most of the information will be shared via code examples and verbally. And I'll be trying to follow the chat as well. So if you have any questions, you can ask them on the chat. And if you address them directly on my name in the chat, it's going to be easier for me to spot them. Just because Zoom done it this way. But also I might spot some questions kept in the common chat. And the thing I'm gonna start with, all the code examples, I keep them in a repository. So right now in the chat window, I provided you with URL for this repository, so you can check it out and you can follow me because I know that sometimes screen sharing doesn't provide very well quality. And even though I will try to use as big font as possible on the screen, still there might be some glitches and so on. So as soon as you know which file name I'm showing to you, you can watch it locally, see it locally, and check out against the source. Also, the repository contains some information in its README file, so I also recommend you to look at it. Good. And actually, it's not the last URL I'm going to be sharing on the chat window as well, so just follow it too. First of all, the question which we must clearly understand, and the question is, what is Raku? I mean, what defines the language? It's pretty much confusing question for most developers. I don't know why. Maybe they expect to see some kind of specification like C++ has, which was total surprise to me when I found out that the specification of C++ is actually paywalled. You have to pay for it. Oops, I didn't know. Okay, good. They have books. Other languages like Rust, they have a book and a manual of some kind, which is official and which is considered, as far as I understand, to be its specification. Raku is totally different, absolutely different. I don't know any other language which does it the way Raku does it. In Raku, we have a set of tests which define the language. If you create a compiler for Raku and this compiler can't pass this test suite, it means your compiler implements Raku language in full. So if you didn't know about it yet, then you can have a look at this URL, and that's where the test suite is kept. We call it roast. And while it might be not so convenient for a human being to read this kind of specification, reading tests is not the best way of learning something. Still, it's fantastically great for developing clean and stable language. It's the best, most definitely. So without roast, I have no idea. Many bugs would just slip away, uncode, and so on. So if you want to learn Raku, of course, you go find some book, you go find some manual, you go find somebody's help. But if you're gonna develop Raku, if you're gonna participate in Raku development, roast is definitely the thing you have to know about and you have to use extensively, and you will actually. For those who are interested in early stages of Raku development, just out of curiosity, it's pretty okay. Java, good. Java has something similar. Well, I'm not a big expert in other languages anyway. I mean, I try to follow, I try to read them, but still. So if you want to see how Raku was developed originally, then you can read those historical design documents on the URL I just provided. And They're actually called synapses. But let's move on. Another thing we must understand about Raku, also other languages has different versions. And Raku certainly has versions too. The first released Raku version was still named Perl 6, and it was 6C version. Currently, we have released 6D version, and 6E is currently in development. So when we technically use 6E, we append .preview to it at the moment because it's not released, it's in preview stage. Also, when we talk about language version, Raku language version, we sometimes use revision term separately. Revision is the letter following the 6. So revision C, revision D, revision E, just where we need some kind of short representation. So if I say language version of or language revision, it's basically the same thing, no difference. Now we switch to implementation. At the moment, the implementation we work on is named Rakuda. It's the primary one. And basically, I would say at the moment, it's the only one. There was some historical, but okay. Oops, sorry, it should have appeared. Okay. If you don't have Rakuda installed yet, I don't know, maybe somebody is total newbie, then you can find information about compiling Rakuda in the README file of my Raku Inside Out repository. That's the workflow I use myself because I work on Rakuda development pretty much lately. So I found this the most convenient way. I use it together with Raku Brew, which lets me to switch between different Rakuda versions easily. So when I do development and I find that something is wrong and I know it wasn't wrong before, I can easily switch to another version of Rakuda and see what's going on. So I hope the README is sufficient and we can skip this step and talk about more essential things. Oh, yes, I forgot to say one other thing pretty much important as I see it. This class, I tried to base it on questions I was seeing from developers on Stack Overflow, on GitHub issues, and other locations. So subjects in this class try to cover those questions. And one of the biggest mistake people often do, beginners often do, they mess up Rakuda version and Raku version. I hope you currently see my terminal window. Yes, okay. So if you ask for a Rakuda version, you basically see, okay, let me switch to a non-build version. Okay, this one is cleaner. So you see 3 lines. You see actually Rakuda version, and the Rakuda version consists of year and months of the release build. And this is compiler version. But the second line, you see the Raku version. And this is the language version the current Rakuda implements by default. This is the language version you get when you do something like this. Say, sorry, I don't often use it. Compiler version. Okay, this is a get compiler version. Yeah. So as you can see, this is what you get by default. This is what your code, language version your code is supposed to comply to when you use a versionless script or code snippet or whatever else. So make clear distinction. We have a compiler and it has its own version. And this version basically changes every month with each new release. And Raku version is something different. It's, well, basically Raku version, it's what is spec'd in the roast. Okay, Raku brew I already mentioned about, and it's also in the README file in the repository. Sorry. And if you want, if you don't want to build Rakuda and you want just use it, of course, you can always go to rakuda.org website and download it from there. We currently have versions for Windows, Linux, macOS, probably FreeBSD, OpenBSD. I don't remember. There should be there. What about other implementations? As I told you, basically Rakuda is for the moment the only one. But historically, there was other implementations of, by then, Perl 6 language. There was Pugs, there was, don't even know how to pronounce it, Nieza, and a few others. If you're interested, you can see this URL in the chat and you can get a bit of history of Raku Perl 6 languages. But we focus on Rakuda implementation. Another question, oops, excuse me. Another question confusing newbies is, after all, is Raku interpreter or Rakuda actually, or a compiler? Well, I already said that it's compiler, but why is it so? You see, when I used this line, it actually acts as interpreter. And also I can, okay, let's do something, whatever. Or you can say it like this, and also you get output of your script instantly, right away, which is more inherent to interpreters, actually. And people expect it to be an interpreter. In fact, it is not. Rakuda is pure compiler. Except that it doesn't compile into a file in some cases, and it doesn't compile into machine codes, into assembler, none of this. Rakuda compiles into bytecode. What kind of bytecode is actually depends on what backend is currently used, what backend you have ordered for your Rakuda compiler. The default backend for now is more VM, which stands for, of course, virtual machine, more virtual machine. This is the most developed, the fastest backend Rakuda has. We have two others. We have Java backend and we have JavaScript backend. I would say they're underdeveloped. They don't support all language features. JavaScript is not capable of threading whatsoever, simply because JavaScript does not do threads. WASM, I hope, but somebody has to do it. I would like to see Wasm to be a backend as well at some point. But, you know, one of the reasons I decided to do this class and to focus on low-level things is because I hope that maybe somebody of you guys presented here may decide to join Raku development, and maybe somebody of you will develop Wasm backend at some point. I mean, the more alternatives we have, the better. But for now, we just don't have resources. Raku core team is not that big to dedicate people to another backend. So at the moment, we focus again on Rakuda, and we focus on more VM implementation of Rakuda. That's the best working combination. Let's talk about the way Rakuda actually is structured. I mean, what Rakuda is composed of. I already mentioned a backend, a virtual machine. This is what actually runs your code eventually. So if you execute your script, it's not Rakuda which executes it. It's more VM which executes the bytecode, which was prepared for more VM by Rakuda and by NQP. NQP is a kind of middleware compiler. It's a simplified version of Raku language, which stands somewhere in between of Perl and Raku, maybe. Not really, it's still closer to Raku, but anyway, it's much simpler, it's much faster than Raku, but apparently it's much harder to write code in because it lacks some high-level constructs we are all used and used to love. Still, we use NQP. First, it was historically done this way, and second, well, NQP is truly faster than Raku, and it's good enough for writing a compiler. And the current design is such that Rakuda cannot compile itself, actually. It's NQP which can compile itself. And when we built Rakuda, yes, this I already mentioned. Yeah, and this I will come to. When we built Rakuda, and if anybody of you tried to build it already, you'll notice that first you see more VM building, then you see NQP building, and then eventually you get Rakuda building. So those are three components of Rakuda, actually. Though each one is independent and can be used independently, but when you compile Rakuda, you can consider them as three components of the same thing. Sometimes it's easier to see it this way. But what is more important is that because all code is compiled into, I mean, all NQP and Rakuda code is compiled into bytecode, it is possible for Raku to call NQP methods, routines, whatever. Just any NQP code can be called from Raku, and vice versa. NQP can call Raku as well. We'll get back to it later in this class, but for now, just remember that there is no walls in between them. They're completely interoperable things, interoperable languages, for that matter. And actually, if anybody ever decides to implement, say, I hate this word, Python In NQP, it's possible. NQP is actually can be used to compile any language. Any language can be written in NQP. It's possible. So if you decide to write Python in NQP, no problem. You can then call Python code directly from Raku, from NQP, from anywhere. So it's, you know, it's the basic principle of bytecode. Nothing really specific here. NQP NQP ops. Yes. Often when you look into Rakuda sources, NQP sources, Rakuda sources, you may see those cryptic NQP prefixed calls, which looks like subroutine calls or function calls, whatever. They are not really functions. Those are low-level operations, opcodes, for that matter. And in a way, sometimes they might be considered like a kind of assembler for Raku, but they are not. Those are pieces of code actually provided to you by NQP. But what is important to know about them is that some of them are mapped directly into bytecode operations. I mean, let me, for example, NQP object ID op, it maps directly into more VM code, bytecode object ID. And some other are actually implemented in NQP itself, and they provide more or less generalized view at some specific data structures or operations or whatever. So just when you see an NQP operation, just know that it's something you get from the lowest levels of the language. And if you want to know what this operation stands for, you can use those two URLs from the chat window. The first one describes opcodes provided by NQP itself, and the second one provides NQP opcodes provided by Rakuda. Again, I'm just trying to prepare you to know how Rakuda is developed, but if you don't want to focus on this, you must not. Simply just for you to know that such thing exists and it's extensively used in Rakuda code. And at this point, we finally start with the actual language constructs. And the first construct we start with is a comp unit, which stands for compilation unit. Some developers, beginners, they meet this term when they start using Raku modules. And often the initial confusion comes from the fact that they start to associate comp unit with a module. No, it's not a module. It's something more than a module. Comp unit is what compiler receives as its input to be compiled. I mean, in this very simple example, in this very simple script, the comp unit is the script itself. Comp unit here starts with this pragma, use v6, and it ends after the last semicolon. And same applies if if you get a module, okay, don't look at the module content currently, but this is our comp unit in this particular case. But this is textual representations, just that we know. Internally, comp unit is a little bit different thing. Oh yes, of course. I forgot to mention this. Okay, this was pragma here. As you can see, it simply says that it's v6. It's traditional for Perl 6 naming, and because it was Perl 6, so use v6 was telling that this file is actually Perl 6. Full version of this pragma looks like this. Use v6d or use v6c. And whether you use this pragma or not, your comp unit always starts with this pragma. If you don't use it explicitly, the compiler will insert it for you implicitly. And because, as I showed you, that Rakuda implements 6D version of language, if you omit this initial pragma, then the compiler will assume that you use language 6D, and it will implicitly put this pragma at the beginning of your comp unit. So it's always there, explicitly or implicitly. Feels to me like I missed something, but okay, hope I'm not. Yeah, it's a bit too early. So getting back to comp unit. Comp unit is a block of code characterized by the language version, which is assigned to it. And it's characterized by the actual code and by one more thing. And here, we need to start with another subject. We shall to talk about frames and scoping. When Rakuda compiles your code, well, actually, would it be Rakuda or NQP, it doesn't matter, but they compile into bytecode, they organize it into frames. I'm sorry, it's, well, another thing just to distract a little bit and relax a little bit. I apologize for any delays or confusions because I haven't had any class in decades. The last class I had was in the middle of 90s, and it was that, teaching ZX Spectrum Basic to 10, 12 years old children. So I'm rather new to this, and also I haven't had much time to train myself on this presentation, on this class. So I just do my best. So back to frames. As I told you, the bytecode is organized into frames. Internally, when we talk about more VM, I don't know exactly how it's done in Java backend, and especially in JavaScript backend. And by the way, talking about bytecode with regard to JavaScript, it's a little bit funny, but okay. I just don't have a better term for what they do in JavaScript backend. So in more VM, a frame, it's a structure, C structure actually. And the structure has several fields which are important for us here and now. It has a lot of fields actually, and it's really a complex structure. But we currently need to focus on just few of them. So first of all, the frame has a pointer to a code object. A code object is actually a byte sequence which represents this frame. Okay, there will be an example later. You'll probably get it better. Also, it has a symbol table attached, except that it doesn't have it attached directly. There is no pointer to symbol table in a frame. It's the byte code, the code object, which has this table, symbol table attached to it. But for us, it would be easier to imagine that symbol table belongs actually to some frame. It will help us to understand some other concepts without getting too much deep into all those low-level structures. A frame has two pointers to other frames. One points to an outer frame, which means lexical, or as we also call it, static chain. So if you have a frame inserted into a frame lexically somewhere, so that a nested frame can see symbols from the outer frame, its lexical relation, and so your nested frame actually has a pointer to its outer frame. And second pointer is to caller frame, meaning that we have here dynamic chain or call chain, call stack for that matter. And as I told you, there are much more other fields, but they are specific to optimization, they are specific to one thing, other thing, whatever. We don't need all this now. Unless you go to help in developing more VM, you don't need to know all this stuff. And well, I just tried to visualize this frame representation. So lexical relation is vertical, call relation is horizontal, and so just if any one of you has better is better with visual information than with verbal or printed information, I hope it will help you to see things like more in perspective. No, I should. Okay. And at this point, it makes sense to see some examples. Okay, for those of you who cloned my repository and want to see those scripts locally, I think you can see a file name down here. You know, all of you probably know Vim, even though if you use Max. So you can get file information from here. Even though I said that I'm not gonna talk about syntax, I still have to touch a little bit of it because some structures, some syntax constructs, they're missing from Pro, for example, or from some other languages. So the syntax which might be new to some here is this kind of variable. So the sigil is nothing new to you. Scalar, it's a scalar. But the asterisk which follows it, it indicates that variable is a dynamic one. And dynamic variable in Raku I'm sorry. It's a variable which is resolved not lexically, but dynamically. In other words, when subroutine bus refers to variable $**foo, it expects this variable to exist in its call stack or in its dynamic chain, for that matter. So when we invoke subroutine foo do declare dynamic variable, then it invokes bar, and then bar calls base, and base should have access to this variable. But when we call bar, it will fail because bar does not declare foo. That's it. The reason of me to show you this simple example will be more clear a little bit later, because we need to understand dynamic variables to understand following example. I'm sorry. Because in this example, I use dynamic variables to demonstrate the difference between lexical scoping and dynamic scoping. So what we have here, oh, of course. Look, when we talk about frames, the closest representation for a frame is actually a block, because block translates almost directly into a frame. But what's even more interesting is that, well, yes, we have block here, which is a frame, and we have a block here, which is another frame. And the way Raku does implement block nesting here is the outer block actually calls the inner block here. I mean, it's literally calls it. There is no any kind of inclusion, Python, so on and so on. A block here is a code object, a separate code object. And with this example, I'm going to show this to you. So lexical scoping, I think it's clear. It's clear here. So the nested block can see this variable here and this variable, excuse me, and this variable here. And please ignore this dump context subroutine, because it contains things which I don't expect you to know yet. So just please ignore it. It's there just to output the information I need. And also I have this disjointed block, which, as you can see, it stays outside of this block, and correspondingly it stays outside of its lexical scope, and it cannot see this variable lexically. And this line is another syntax trick of Raku. So here I store this disjointed block in a variable, and here I call this block manually. I think it's pretty much clear. And now look into the output. Because there is no easy way to distinguish one block from another block, one of the reasons why I use dynamic variables here is because when I see this variable in a table of symbols, I know that this symbol table belongs to this particular block. Okay, hopefully it's clear. And wait a second. Yes, the first output, block of output comes from this call to dump ctx. This is the first one. And what we see here, this is a frame. So the innermost frame is 0 and so on. The outermost has the biggest number. So we see that this is the inner block B2, because we have B2 here. Then we have its outer block, and then we have comp unit address space, because comp unit is also a frame. Actually, I was going to talk about it later, but somehow naturally it fits here. But this is lexical relation. And when we look into call stack, we see totally same structure. We see nested block, we see its outer block, and we see the top level, the comp unit. So as I told you before, blocks are implicitly called when they used in sync context. Okay, just let's keep it for now. When they are used like this. So this block is called by comp unit, and this block is called by its outer block. And this exactly what we see with the first block of output. But then we call the disjointed block, and it also dumps its symbol table. And when we come to this dump, which is the second output block here, we have completely different picture. Because as you can see, we have only two lexically nested frames. We have actually the disjointed block frame, and we have comp unit frame. And this is lexical relation which we really have here, because the block is here and the comp unit is its outer. But the call stack, yes, we have disjointed, we have the nested block, and we have the outer block, and then again we loop back to the comp unit here. So with this example, I hope this example makes visualizes two principles pretty much well. The first principle is that one frame, one block in Raku actually calls any nested block in it. Actually, the picture is the same if we do it like, if we add a conditional statement. Sorry. So over here, it's also the same. If condition is true, then call this nested block. So we always call, always. And the other concept which I hope to make clear is how the dynamic linking, dynamic chain is used to resolve dynamic variables, because as you can see, please ignore the unit marker for now. I mean, I'm not going to talk about it directly, but this is a subject I'm going to touch a little bit later. That's something interesting as well. So lexical and dynamic. Lexically, as I said, lexically disjointed block cannot see symbols B1 and B2. But when dynamic resolution is used, as you can see, they're accessible. And if we do it like this, I will uncomment this line here. And repeat. And here, when disjointed block is invoked, you see it outputs second block. This output comes from this line here. But if we invoke this block individually from the comp unit level and repeat the script, oops, that's because dynamic chain is different in this case. So if anybody has any question at this point, I'm ready to answer it before we move on. Okay, probably no questions. So why all this is important? It's important on its own. But aside of this, it allows us to better understand some other principles of how Raku works and how it's built. As I told you, comp unit is a frame. So when a compiler starts compiling your comp unit, it creates a frame for it, separate frame. And as a frame, it has its own lexical scope, and it also has its own dynamic scope. For now, we're going to talk about lexical scope. And the lexical scope of any unit, we call it setting, meaning that it's a setting in which a comp unit operates. By default, Raku installs its core as comp unit's setting. And core is actually a kind of standard library of Raku language. I'll have a little bit more about it, but say, oops. Over here, when we use say, we actually call a subroutine which is defined in language core. So it's not a statement. It's a symbol which is available for our comp unit lexically, and actually not only comp unit of code, but to any code. And the next thing which worth mentioning is that core is different depending on what version, language version, you have requested. Now it's time for some more examples. We are going for core settings 0 to start with. Again, I'm not showing this code to you because it's beyond the scope of this class, but still I had to do it to show you this core setting 0. The hidden code actually dumps all the symbols it can find in lexically outer spaces of our comp unit. And what symbols does it dump? Well, you see grep here, you see say here. You probably will find some other familiar symbols here like tangents, whatsoever. So those are symbols provided to us by 6C version of core, Raku core. Excuse me, some questions. Oh, yes, I missed a question. Sorry, about coroutines, the question about coroutines. Well, basically, frame is pure technical thing. No, frankly saying, I'm not ready to answer this question for now, because coroutines has a little bit different meaning in different languages. And so if you want, we can try to discuss it a little bit later if you provide me maybe with some example or something like this. We have a kind of coroutines in Raku, actually. We do have them. And when you're gonna study supplies, for example, then basically that's what happens there. It's supplies are using some kind of coroutines, but not the way they're defined in other languages. So I'm probably not ready, really not ready to cover this subject. So let's get back to core setting here. As I told you, core setting is available to our code lexically. So we found all those symbols. And one of the symbols provided by core settings is this constant. And this constant tells us what core setting we are currently using. So, for example, this is another dump, very much simplified, of our frames. So we start with compunit frame. Then we see some empty one. Don't ask me what is it. It's beyond our discussion. And then we see that the constant core setting ref contains C. C is because we requested 6C language version for our script. If we switch to 6D, then we see D, but we also see C in the next outer space. And this is what you're going to expect with 6C language version as well. So what I'm trying to show you here is that those are still frames. The innermost, which is our comp unit, outer frame, another outer frame, and so on, so on. So basically what we see here is that 6E core setting, it's actually lexically scoped by 6D core setting, which is in turn lexically scoped by 6C core setting. And lexical, oh, it's different. Okay, I will come back to this example in a moment. For now, I want to show you this because text form is probably not easy to read and not easy to grasp without understanding the code which backs this output. I made this pseudocode example. So in this example, as you can see, our comp unit is represented as a block. So this is our script. And in this script, we request for 6D version of Raku language. Apparently high volt, yes, it used to be. And since we requested 6D, our comp unit is installed inside another block, which is actually implements 6D core. And 6D core is implicitly installs 6C as its outer. So this is the structure of our typical comp unit, a typical script in this case. Why is this so important to understand is because when we have a feature which is implemented in later version of Raku language, but is not implemented in early version, usually this feature is represented by a dedicated symbol. Would it be routine, constant, some kind of type object, some kind of class, whatever. We included into core, which corresponds to the language version for which this feature was implemented. And if the very same feature was implemented differently in earlier language version, then newer version would just lexically override the previous version. Like on this diagram, you can see that core setting rel is actually represented in both core settings, in 6D and 6C. But when we request it in our code, we take it from 6D because it's lexically closer to our comp unit. Okay, hope it's clear because you know what makes Raku approach in this respect different to languages like C, C++, and whatsoever. The standard library do not export symbols into your space. Instead, you have lexical access to the symbols in your standard library. I mean, the difference usually is not that visible in code, but it might be pretty important at times. So it's very nice to know about this. Very useful in first place. Still, there might be a confusion about this pseudocode as well. As I told you, nested blocks are called directly by the outer blocks. So one may expect that in this case, our 6D core actually invokes comp unit. But that's not the way things work here. If you take core settings 2 example from the repository and call it, then yes, you can see lexical outers. We already used to them, so we have comp unit frame, and then we have 6C settings here. But when we dump the call stack, we see absolutely different picture, and we see no any core symbols here. There is no single core frame in the call stack. And I'm gonna reveal a little secret here. All the frames we see in call stack, they all belong to our compiler, actually. Just without focusing on those particular symbols and frames, What happens inside? Okay, back to this. Sorry, let me skip this page and go here. It's a little bit less information and a little bit easier to see. So the way the compiler works, when it loads a comp unit and finishes compiling it, it forcingly sets the lexical outer pointer in our frame structure to the frame which belongs to the core setting. I mean, its compiler does not invoke the setting frame. No. When it comes to invoking user code, the compiler invokes directly comp unit frame. So I'm afraid I'm messing up here and cannot. So there is a way to take any frame and explicitly tell that your lexical scope will be this frame. You can do it manually for any kind of frame. And the worst case scenario, you can even do it runtime, so that your block, for example, may get different lexical scope in different situations. It's possible. It's doable. It should be avoided, but it's doable. And yeah, it's the same situation about core setting. But what it means to us when it comes to language versions and how it affects us? Here I have another good example. Quite recently, Elizabeth Matheson has implemented last statement with a value, which means that we can actually stop grep looping over a list of values whenever we need it. Yes. I'm sorry. Yeah, I have to switch to. Okay, now I'm really using the latest version of Raku. So as you can see, our output stops at number 19. This is because of this condition here. If you just avoid doing this last, you see we get prime numbers up to 47. So with this last false, we can stop at any moment we want. And this feature is only available if we use 6C. And if we switch back to the default 6D, yep, apparently we get an error here. Because 6D just doesn't have appropriate implementation of the last subroutine. Okay, and And this is a file from 6E core, where you can see that new implementation of the last subroutine exists. And from its signature, you can see that it's accepting an argument. Okay, so at this point, we are done with cores and frames and so on. And so if you have any questions, I see one question. Last false. Yes, last false. The logic here is that, okay, if you remove this line, what happens? We iterate over first 50 numbers, and then we check if an element from the list is a prime number. And if is prime returns a true value, then this block returns a true value, and grep knows that the current element is accepted. Contrary, if is prime returns false value, grep knows that this value must not be included into the output. But last means that we end current block, we quit current block, and we want a value to be returned. And if we return a true value, it actually tells grep that this number is acceptable. And so you see 20 to be included as the last element, even though it's not a prime number. That's because last simply supplies this block return value to grep to be interpreted. I do false because I know that 20 is not a prime. More correct implementation would be last is prime. So it works as expected. Last true if, well, one way or another, yeah, it might be confusing. I mean, to me, it was pretty much clear, no problem at all. But if you don't know, if you're not used to those things, it really might be confusing at times. Okay, if no more questions here, then let's move to the most advertised feature of Raku. Everything is an object. Literally, everything. Actually, if you get back to this example here with disjointed block, I already started using this concept of Raku because I don't remember. Yeah, in Perl, it's not possible to assign a block to a variable, and apparently it's not possible in C, but in Raku, it's a normal thing because block is an object. So partially, I have already started with this, but there are more than that. And yes, when people hear about Raku, often they start knowing it with this statement that in Raku everything is an object, just everything. It's about the same thing I started looking at Ruby some years ago. And because everything is an object, everything can be introspected with different kinds of methods. And Raku has a vast majority of methods to find out what object do we deal with, what this object has, what properties does it have, and so on, so on, so on. But at the moment, let's start with the most basic methods, what and which. So the most simple example is to tell you the difference between those two methods. What tell us what type our object has. And it's not just tell us the type of it, but it actually returns the type object. So if you look at this line of output, you see that int here is enclosed into braces. This is typical representation for type objects or for classes. For example, if we do something manually, as full, say full, you see, we don't create an object of class full, we just report itself, and that's how it reports itself. Which tell us a little bit more information. In this case, which tell us that we have type int and it's undefined, meaning that it's a type object. Now, if you move further down of this script, we see that we initialize the variable with a number and we repeat what and which again. And what we get here, what didn't change because it always returned just type object. And which tells us that we do have int, but it's initialized, it's an instance of int, and its value is 42. So I use which on many occasions when I know that something goes wrong about my code, and I want to see if some object is already initialized and if it's not. And another thing about which, this long number over here, it's so-called object ID. So every object in Raku has some ID associated with it. A particular value of this ID depends on the backend. For more VM, it's this long number. Don't think of it as a memory address because it might be a memory address or it might be not. It's not guaranteed. But what is guaranteed is that it's going to be unique for each unique object. And so when I know that something goes wrong in my code and I see different data coming from seemingly the same source, I often use which to see whether the same objects are actually coming to the problematic location. And often it helps so that I know, for example, if I throw an event object over here, then I check it here in my code, here and here, and I see that it's all the same object. It has same object ID. So I know the path my event object goes through the code. Okay. But which, as you can see, which output is different for initialized values, for instantiated values. And in this example, I simply want to show you how it differs. And So we apply it to a string. And here we declare a dummy class foo. We create an instance of this class and we report it. And again, because everything is an object, you see, I use method say to output it. I simply chain methods in one call. So we see here string is reported as string class which has value foo, but for class foo, again we have class name, but as you can see there is no u in front of the object ID, and because foo is not a value object, I mean it doesn't have any particular value associated with the object. It is reported by its object ID, not by the value. So that's how which introspection works. Also, if you get back to that example with lexical and dynamic scopes where I take a block and store it into a variable, as I told you, it's an object, so it can be stored. And in this example, we see that if we declare a block like this, but then we call a method on this block, this block is not called. We got this block reported with which method here, but the code of this block, which should have reported as p constant, it never was called. Just, you know, to combine two subjects together, to link them to each other. And I love tricks. I mean, I don't like using them in real code, but I love tricks because they reveal some really deep behaviors of the language. And in Raku, we can find out that a label is an object too. I mean, really, everything is an object. Just everything. If you run this code, look, label instance. So the symbol foo, then we use it in the say the switch and get this output. And then we ask this label object to stringify itself in a human readable form with gist method. And here what we get of this gist method. Well, actually more correctly would be to say this is the output. So you see a label object knows where it was created, line number 4. Yes, line number 4. And it knows the context in which it was created. So it keeps a number of symbols before the label and a number of symbols after the label. Okay, yes. We also have another pretty much popular introspection method, .how, but we will come to it a little bit later. For now, I think I'm done with this topic. And before I proceed further, if there are any more questions, I will try to answer them. Okay, probably not. So we have a question after all. Okay. Daniel, I think you can unmute your microphone and say your question.
I vaguely remember something in the documentation saying that variables and scalars break the everything is an object rule. Is that true, or is there anything you can say that would sort of illuminate that?
Sorry, Daniel, could you please repeat?
Sure. This may be incorrect, but I remember something from the documentation saying that the way Raku implements variables with, and especially scalar variables, breaks the idea that everything is an object. Am I remembering that incorrectly, or is there something to that?
Daniel, you're currently running ahead of the train.
Oh, okay. Well, then never mind. I guess we'll get to that soon.
Yes. When I get to this point, it's going to be a lot of things to say about, really a lot. So.
All right. I'll look forward to that in a few minutes then.
Thank you, Daniel. Okay.
Vadim?
Yes.
This is Bill. I was doing which-3, and I wasn't sure whether it was giving me an error there. That little up arrow symbol. Is that not an error?
No, it's not an error.
Okay. Okay. All right.
It's,
well, I'm reproducing what you say. I just go ahead.
This label, actually, it's no wonder that you've got confused with it. When I first wrote this example, I was also thinking that, oops, it's an error. But the point is that label just uses this Raku convention to report the place where it is located. And that's it.
I see.
I mean, all this output you see here, it comes from gist method of the label.
Okay.
This is, we can do it like this. And actually, we can remove this gist because this is what say does for us implicitly. Just for information. Because say doesn't output things as is, it stringifies them first, and it stringifies them using gist. And okay. So here is the angle brackets, the opening one, this one, and the closing one.
I see.
And everything what is between is label stringification.
Great. Thank you.
Yeah, welcome. Okay, meta object protocol. When I was preparing this class, I digged a little bit into the history of meta object protocols, and at some place it was said something like all languages implementing the principle of everything is an object has some kind of meta object protocol. I don't know how much true is it, but well, at least I know that the concept comes from common list and Smalltalk. And then where I first met meta object protocol was Moose in Perl, Moose framework, and a little bit of Moo, but in Moo it's hard to call it meta object protocol anyway. It's pretty much specific. Anyway, so Raku has its own meta object protocol, and it's very standardized. It's not spec'd in Rust completely. We do have some bits and pieces here and there, specifying how to use a couple of meta-object protocol methods, but largely it remains unstandardized. For me, as for a developer, it's good because often I can change API without worrying that it would break the specification. Though it might also break ecosystem modules, but this is being closely watched by release manager. So he won't slip any breaking changes into the language. But the bad thing is that if you use some features of mob in your code, you are very likely to be on unsafe side of the things, because API might change and your code might break. So mob is very attractive for doing different kind of things. I will show some of them later. But when you use it, be careful and be prepared that you might get some problems. Okay, enough about bad things. Let's talk about great things. Where previously I was talking about Rakuda structure, it was about the way we compile Rakuda. Now I'm going to talk about Raku implementation structure. It's a little bit different thing. Raku implemented by three major components. First is, of course, a compiler. Compiler as such, as you know, the object which takes your source code, produces, parses the syntax of your source code, and generates code for it. How it does generation, that's currently beyond this topic. Meta model, which is actually the implementation of meta object protocol, is responsible for type system semantics in Raku. Okay, yes, anyway, I'm going to talk about it. So if you don't really understand what does it mean, just ignore it for now. And core setting we already know about. It's our standard library. So example is, okay, let's take this example. So over here, when we see int, we know it's a class, and we know that there is some meta model code which actually implements this int. But also we know that int itself is declared in the core, in the language core, in core settings. So keeping all this in mind, and of course, compiler has to encounter this int symbol in our code. It has to find out what kind of symbol is it and how is it responsible for doing things. And well, what the hell? Like int, you all know what int is. Why do you ask me, compiler, to do something about it? Yes, because we know, but you don't. You have to find out, and you have to handle it correctly. All three components are pretty much tightly interweaved to each other. I mean, you cannot pull any of them and separate it from two other components, even though those ties are not frequent in some cases, but they're strong enough for us to not be able to separate them. So again, when we talk about Raku, we basically keep in mind those three components. Meta object protocol structure. Not the best topic name actually, but okay, let's go with it. So as I told you, int is backed by some kind of meta object code. As a matter of fact, the precise definition would be any class, any type object, sorry, no classes here, just type objects. Any type object is backed by an instance of meta object protocol class. And this is what we get when we use .how method. How 0. So if you look into this example, you see I apply how method to different kind of objects and type objects. The last line, just ignore it for now. And here is the output I get. So string, it's actually a class type str, and it's backed by class how. True, this might be not really expected by some, but true is actually an enumeration value. Int, it's also a class. But unsigned int, it's a subset. So unsigned int also comes as a surprise to people sometimes. And why do I have this second int here? Just by mistake. Okay, I don't need it here. And if you consider this output, we see all this .new appendix. This is how Raku default stringification in GIST tells us that in this case, we are being reported with not a type object, but with an instance of this object. Here, in other words, this suggests that at some point, class how was instantiated with .new method. To check it, I use this last line. So I use method defined, which will tell me that what .how returned to us is actually defined. Just to show you that it could be different, you int defined. So if I apply it to a type object, to a bare type object, we get false because it is undefined. And undefined in Raku means it's a type object, and defined means it's an instance of this type object. Now, let's have some fun. So, when say reports a class to us, as I already told you, it uses method gist to stringify it. But what happens inside? Inside, Raku code actually uses meta model to find out what the class name is. And this is how we get the first line here. It's .foo. But since meta model knows what the class name is, then we can change it. And here is our second line of output, which is foobar. Wait a second. But I was asking for foo. But you give me foobar. That's because what we see here in code is for your eyes. and things are somewhat different internally, and later I will come back to this subject as well. So, but for now, let's just accept the fact that we can change a class name on the fly, and this change will affect our class immediately. We can rename it. We can rename the way it gets reported. This line is actually the same as this line here. It's just another syntax used to access metamodal methods. This operator is called meta method call operator. What it does, it's just a shortcut to apply .how method, and by convention, most of metamodal methods accept the type object itself as the first argument. So the method call operator does this for us implicitly. It takes the object it's invoked upon and uses it as the first argument of set name here. So it's really convenient thing, because you see, even in this simple case, it's already, two verbose. We have to call how, we have to remember to pass the type object as the first argument, whatever. But what if we have something like, I don't know, .int, we convert a string into int, and then we would like to call some method on it. So we would have to do it something like this. Just for example, it's too much handwork and stuff like that. And what if I need not int here, but the object itself? Of course, it's much easier to do it this way. Just a convenient shortcut. Good to know, because you're likely to use some methods in your code. Very likely. I mean, even though I'm not going to do some kind of development for Rakudo or Raku or whatever, at some points you will use methods. Oh yes, thank you for the link to documentation. Actually, I forgot to put it here. Now, well, actually, this bullet talks for itself. The entire metamodal, as well as Rakuda compiler, are actually implemented in NQP. It is possible to write some metamodal code in Rakuda as well, but and this ability is used by some third-party modules, some ecosystem modules. It's especially fantastically great and so on. I don't have enough words to express it. It's used by ORM called RED, database framework. And it's used so artistically and so, I mean, it's just pure pleasure to use this framework to work with databases, believe me. And it's fully apparently written in Raku. But when it comes to Rakuda implementation, in Rakuda metamodal is all NQP. And yeah, I also refer to this note I made earlier that NQP can call Raku and Raku can call NQP. So this is used in metamodal. And as you can see here in this example, set name is actually written in NQP. As simple as that. And NQP itself, as I also mentioned it earlier, it's a simplified version of Raku. How much simplified? Well, it is sufficiently high level to implement the principle of everything is an object too. So in NQP, everything is an object as well. And therefore, NQP has its own metamodel. And so we get deeper and deeper in this rabbit hole. This is what my next example is about. Look, first line, we get metamodel object for number 42. And then we ask about metamodel object of the metamodel object we've got in the first line. And then metamodel object of metamodel object of metamodel object, and so on, until the last one. You know, the house which Jack built. Gives us this one we already know about, class how. Then we get in QP class how. This is metamodel class for Perl 6 class how. But then we get some strange one, know-how. And then we get know-how again. And if we add one more how to this chain, we get know-how again. So we get into infinite loop at the end. What's happening here? As I told you, NQP is capable of building itself. But first, it has to bootstrap itself. And, you know, it's chicken and egg situation where there is no clear way to create a class without having a metamodel for it. And metamodel requires classes, which again requires metamodel. This situation has been solved by one single requirement to the backend virtual machine. It has to provide a type which is sufficient for itself. A type which has itself as its own metamodel. It can do nothing except of method how and method name, as far as I remember, maybe. Both methods are implemented by virtual machine, purely by virtual machine. And then we use this class to create our first level, the deepest level metamodel class. If it's not really clear at this point, don't worry. I mean, I mostly tell you for avoid any possible confusion in the future. But this piece of code I would like to show you. This is a source file of NQP compiler. And yeah, this is our first metamodel class declared in NQP. It is declared as some weird kind of thing, know-how. So if you ever get so deep in introspection, at least you won't be scared about those things. Do you need this information? I don't know, but at least you will know how to use it if you ever need it. Three examples. Okay, and I have one more example left, yes. I told you that it is possible to write meta model in Raku, but it is also possible to modify a meta model in Raku. Look at this example. We have class foo as our laboratory mice here. We have a role, skip it for now, and we have some say and so on and so on. The piece of syntax I would like to explain to you is this one. Does, in this context, mixes in role my how into the class on its left-hand side. So basically nothing, it's, in a way, it's something like saying, so something like this, except that we do it runtime. This is a kind of thing Raku is really great about, because you can do pretty impressive things just at runtime, even though you have compiled code. You can modify it in so unusual ways, and it's supported and it works clearly, and it doesn't fail you. In this role, I define a method short name. Actually, short name is the method which is used to stringify our class. And when I mix in my role into the meta model class here, I actually override this short name. You see, first line comes from here. Then I apply the role and do it again, and I get different output. In a way, it's also some kind of trick, but as a matter of fact, this behavior is often used by many modules, and especially it is used by traits in the core and so on, so on. So if you read about traits, then keep in mind that many of them actually modify your meta model object in similar way to what I have shown you in this example. Good. So far, so good. Just a list of methods which I used most and which you may consider very useful in your code often. Name and short name, I told you about. They return full name of type object and its short name. Let's not focus on this, but let's pay some attention to MRO method. And MRO actually stands for Method Resolution Order. What it means is when we take those two class declarations, where it's clear that class bar inherits from class foo, and then we ask bar about its method resolution order. This is what it gives us. It gives us bar, then it gives us parent foo, then any, then mu. This is the order which is used by Raku to look up for methods. So if you do something like bar say, what happens is Raku goes to search for say method on bar. It's not there. Then it switches to foo, say it is not there, and then it switches to any, and any has method say and. So we found the method object and we can invoke it. This is really important thing because one of the problems about C++ was always their inheritance, multiple inheritance. It wasn't really clearly specified which way the inheritance works. It wasn't really well thought out, and it was causing huge amount of problems to developers. That's why we got Java, and really, I don't like Java as I don't like any language which dictates to me how I write my code. If I want multiple inheritance, I want to have it. Raku didn't go this way, luckily, and in Raku it was specified that we don't consider inheritance. Instead, we use inheritance to build a specific order of classes which we then use for method resolution. And since the algorithm behind this resolution is known and published, we know exactly how our code behaves. If you want to know more about it, you can find more information on the network, you can find more information in the documentation. But believe me, quite often you may need to ask your class about MRO to find out why you get not the method you expect to get in one or other situation. And there are some other cases where you would need it. Another thing. Sorry. Look, when we declare var, we explicitly define that its parent is foo. But for foo, we don't define any parent whatsoever. What happens in this case? The compiler implies that any is the default parent of any class which do not have any explicit parent defined for it. So whenever you create your own class, just know that you inherit from any, and all methods available on any are going to be available on your class too. Hopefully that's as simple as that. There's no really any tricky part here. Methods. Methods actually return you methods defined on your class. There was a recent discussion, and there is an issue on GitHub about stringification of method objects. So over here, I use explicit call of name method to make things really, nicely visualized. So if you consider this example without my participation, just keep in mind that if you just dump the list of methods returned by this meta method, you might get a little bit garbled output in the current version of Raku. We look at another thing. So those the methods defined on class str. I'm sorry. And alongside with methods, meta method, we also going to be using can meta method too, which is, I think, also its meaning is pretty much clear, but its semantics is different from you might expect. Look, for UC method, yes, str can do UC, which stands for uppercase, but you see we get a list of method objects. We get 2 UC methods. Why so? It's because there are 2 UC methods. One is defined for str and another is defined on name. But for us, it is important to know that can does not return a Boolean value. Moreover, we must remember that NQP doesn't have concept of Boolean. As in Perl, it uses implicit Booleans like 1 is true, 0 is false, and so on. Defined is true, undefined is false, and so on, so on, so on. And next line, we ask for foo method, which is clearly not defined. And can gives us just empty list, which is also false in Boolean context. Like this. We make it Boolean. And so you can use can to find out if your class or somebody else class is capable of some method. But just remember that it doesn't return Boolean. It returns a list, and in certain context, this may come out as pretty much a surprise. The next example I better skip for now. So we have methods can. Find methods is in lookup are 2 other methods from the very same family, and they have different semantics, and I think it's simply too much for now, and it's time to switch to another subject now. So do we have yeah, questions? Methods. Oh yeah, yes, I meant exactly that issue. Dot methods. Well, Daniel, it is possible, I know, but I'm trying to use as simple syntax as possible, just not to confuse people. But yes, thank you. Good. Good. You know, when I was preparing this class and this presentation, I wrote a note to myself for this particular page that, okay, let's get some rest and change the subject. Because, you know, we get focused on one subject for a long time. It's going to be too much for our brains. We need to rest, to have some rest. When I finished this subject, I just found out that it's much, much bigger than anything we had earlier today. It's really a huge one. And everything I told you before, it was driving us, guiding us to talk to this subject in the first place. Symbols and containers. And let me use some clickbaiting. Raku doesn't have no variables, nor subroutines, nor functions. Footnote, not in the classical meaning of the compiling languages. You know how they do it in advertising, you know, big font, we do it for you free. And a little bit footnote, oh, well, with a little bit of monthly payment since a certain period, for example, whatever. So why generally this statement is not true, there is some reasoning behind it. And yes, I promised not to talk about my variable equals 42, but I'm gonna talk about it, just from different perspective. For example, I'm gonna talk about it from this perspective. As you can see, I use two different segment operators here. The first one is actually a segment. The second one is called binding. Here is the example code which explains the difference between the two ways of initializing a variable. So what we do here, I assign 13 to full, we bind bar to full, then we assign pi constant to full, and then we report those variables again. Really simple. And many of you has probably guessed, even if you don't know what this binding operator is about, you could have guessed the outcome. So, in a way, one can say that with this line, bar became an alias to full. So they became basically the same thing. And the rest of this topic, I'm going to tell you what's exactly happening here and how this binding implemented and what consequences it has for your code and, well, basically for any other code. So let's start with pretty much familiar syntax to the most of you. Any language, many languages, where they use the concept of namespaces, use double colon for name resolution syntax. So if you group your symbols into modules, packages, whatever they call it, when you reference to this namespace from outside, you use double colon to find a symbol there. For example, in Raku, we declare a module. And remember, as I told you, that comp unit is not a module, which is sometimes confusing people. Well, here you see we can declare a module pretty much everywhere, no problem. We just create it whenever we need it. Inside this module, we declare two public symbols. Our here stands for public, contrary to my, which is lexical scoping and which binds a symbol to a particular lexical scope. And we just resolve those symbols. Oh, easy. This is subroutine call. This is variable output. Those two lines here. But in Raku, everything is an object. And full double colon is an object too. And it actually represents the symbol table which is associated with our module. So remember, as I told you, when we were considering frames, I told you that there is symbol table associated with the frame, and this symbol table directly belongs to the code object. So when we declare a module here, we actually declare a code object for this module. And both variable bar and subroutine bar are getting installed into the symbol table of this code object. And what happens then? We have access to those symbols via a data type called stash. Excuse me, like this. So here we introspect the full double column, and it tells us that it is a stash instance. Stash, I think it's easy to guess, it stands for symbol table hash. And if we use MRO to look into the inheritance of stash, we find that it actually inherits from a hash. And therefore, we can use a stash instance as a hash. Okay, just very briefly, .who is another introspection method, and it's actually the method which returns us the same stash. So you can see it over here. And from object ID, as I told you, I use object ID to identify same objects. So foo.who and foo double colon, it's the same stash. So use whichever one suits you best. But from syntax point of view, double colon is usually much more expressive. So we are getting back to our module foo. And because foo double colon is a stash, which is a hash, so we can ask for its keys. And here's what we get. Remember, we have declared two public symbols, variable bar, scalar bar, and a subroutine bar, which, as you can see, represented as ampersand bar, because ampersand is the sigil for code objects or for callable objects. Okay, and because these two lines here simply to demonstrate that stash is really a hash, because I just, take a dummy hash and also used .keys with it to see for its structure. And as you can see, we have two keys, A and B. Here is A, here is B. For which, well, here it goes, for which, you see the reason I enclosed it into braces is just to visually separate. Because basically, this is the same. Okay, so stash is a hash, and this allows us to write this line of code. So we can assign a value to a key in foo, except that anybody noticed that there is no declaration for scalar foo in module foo. It simply doesn't exist. again, same output because it's the same script, but you see, it doesn't fail. Moreover, when later we resolve scalar in full namespace, we get it. So this one here, it stands for this output. So guess what? We just created a variable manually without declaring it. And it's available. It's available for use. That's a feature of another great feature of Raku, because again, despite of being compiling language, Raku allows for a huge amount of dynamic operations, dynamic changes in its code structure, in its data structure, in many, many other things. And by the end, if we dump symbols from the stash, yes, we do see a new variable in there. Is it? What exactly is instantiation? Sorry, I just don't understand what this last question means. If you could please elaborate, I would gladly try to explain. Meanwhile,
Yeah, trying to the foo, the $foo scalar that you said wasn't defined, but you're able to get the one out. Is that instantiation? Is that just does Raku understand that you want that variable there?
no,
Line
doesn't
16
understand.
where you are. Line 16 where you are in this code stash 2.
I just create a new key on the stash, and
Okay.
this code below. This is not an instantiation. I would rather say that it's auto-vivification.
Auto-vivification. Sorry, that
Yes.
very good. Thank you very much. Thank you.
Yeah, you're welcome. But still, keep in mind that when it comes to this line, you see Raku does not resolve this symbol statically at compile time. Instead, in this location, it is Raku the compiler inserts bytecode which dynamically resolves a variable. This is what makes this kind of things happen. So in a way, yes, we not only auto-vivify a key on the stash, but in a way we can say that we auto-vivify a variable in this module.
I see. Great. Thank you very much.
You are welcome. And let's this will come to later. Yeah. Aside of custom modules, okay, let's make it not that confusing. Raku actually has two concepts, similar concepts. It has packages and it has modules. They are very much similar, but they're still different. Package just declare a namespace. It's low-level thing. Module, it's module inherits from a package, and it does a little bit more things. It has more functionality. So sometimes I'm going to be using package word. So don't be confused. Package usually refer to low-level namespaces used for specific purposes. In this example, we have one of those namespaces. This package named global. Global is our comp unit, primary comp unit namespace. And when I say primary, it really means something, because there might be, I don't know, hopefully word subsidiary would be the right one. So kind of subsidiary comp units. If you use this keyword in another place, it would still refer to the main, to the primary comp unit. Let's see. First, the simple case. So at this line, we see again I dump keys of this stash. And what it gives me class full, and it gives me hash percentage. Because here we have our hash, and here we have our module. So far, so good. But here, let's complicate the situation a little bit. I introduce a module which is defined in a separate file. And look, I also define a variable in this module, then I declare the module itself, and then I declare a subroutine which would dump this global namespace for me. And what I get, I get the same global as I had in the previous example. So when you ask for global namespace in your module, you actually get it from your script which consumes your module. Okay, but then we have globalish. Globalish, the name means that, well, it's kind of global, not totally. And globalish is our modules, component namespace. And again, don't mess it up. It's not modules namespace. It's the namespace of the component where our module is defined. That's why we see this variable module sorter and stash for the symbol. Module sorter and stash for. It's a way for simplicity. Okay, you remember that if we declare something as our, it becomes public in its namespace, and it should be available on the stash. But as you can see, we still don't get it in the output, because again, it's not globalish, it's not component namespace, it's modules namespace, and we don't dump it. Global has one unusual specific, actually. Let's modify our script. Global. Nothing really confusing here. As I told you, we just create a new variable in the global namespace. Good. So guess what? We get a dynamic variable. The point is, any variable declared in global namespace is accessible as in the dynamic scope of any module, any code we use in our application. This is pretty much obscure thing and not well documented. So since I'm telling you all this tricky stuff, I have to warn you that if you're gonna be mangling with global, you better not. Just better don't do it without clear understanding what exactly you do. Because this might have some very unpleasant side effects. For example, you can create a variable on global, and some module you use in somewhere inside is using the same name variable just by accident. You know, simple semantics, simple names. Well, just inside it, and somewhere this module is expecting the variable, the dynamic variable, is to be uninitialized, and then it accidentally finds it initialized. Kaboom! Problem. And really, it's a kind of problem which is very, very hard to be traced down. We actually have another namespace for this purpose. We have process. And this namespace is, yeah, I think it's process. Yeah. This one is documented. And its behavior is also well documented. So if you need to create a custom dynamic variable which is accessible globally, then do it in process namespace in first place and well document this behavior. Everybody must know that you use this variable in your code, because still it's not safe. Still there are clashes possible. Aside of stash as such, which represents real packages and real modules, Raku has a set of pseudo packages or pseudo packages. Those are really useful for introspection. For example, my. It's the simplest one. My gives you symbols available in your local lexical scope. And when I say local, it's really your innermost lexical scope. Look at this output. We have buzz and we have $_. This one is implicitly defined for us by the compiler. So here is buzz variable, but no bar, because bar is our outer scope and my does not see it. Well, it looks pretty much useless at this point, but it has some use. We'll get back to it later as usual. Let's introspect this pseudo package and let's see what is it. Oh yes, it's a module. It's a module. So as you can see, my is also a type object because it has a meta model representation for it. and my double column is a pseudo stash. Pseudo stash is an object. Oh, I forgot to provide you with MRO. Okay. Pseudo stash is it's not a hash. I forgot. It's a map, but one way or another, map class is immutable version of hash. So don't be really confused. Think of it as a hash anyway. Pseudo hash is different from the stash. Oh, pseudo stash is different from the hash because depending on how which flags were used to create an object, an instance of pseudo stash, it will collect and provide you with information about symbols available in certain namespaces and in certain conditions. It's an extremely powerful tool for introspecting symbol tables. Good. For example, color, it's another pseudo module. And color tells you, provides you with namespace of your color. Well, actually, the name tells you about it. But what is more interesting is that we can chain pseudo modules one to another. So here, the semantics of this line is give me my namespace of my immediate color. Here's the symbols we get in if and din. And we get them because bias is called over here. And in my scope of this condition, we only have din and we have an if variable. So using pseudo modules, you can find basically any symbol in related scopes. Would it be lexical scope or dynamic scope, whatever. Like, for example, we have lexical pseudo module. And lexical gives us symbols lexically visible. And if you look at the output of it, okay, skip all those special variables pre-installed by compiler. But lexical also can see foobar. And foobar is actually defined here. So what happens here is that lexical traces the lexical scopes of this call site and collects symbols available over here in this scope. Okay, you can ask me why bar is not here, because really, as you can see, it's not here. I must admit I don't know exactly. Unfortunately, when I was doing this example, I got a little bit confused and we need to clarify the exact meaning of lexical. The documentation says that lexical returns dynamic symbols. So this variable must not be included into the output. But unfortunately, we do get it. And my understanding of lexical is that it must return all symbols lexically visible in a particular scope. So bar should be visible, but it's not there. So it's just a new bug I discovered, like, before yesterday, maybe, I don't remember. And I will probably have to address it later. Still, anyway, you have it. And at some point, it will work exactly as it should. Do you have any difference? Yes. Pseudo stashes behave a little bit differently in different language versions. Until 6D, there was some glitches in pseudo stashes implementation, which I addressed in 6E version. So have a look. This is what I get when I run my code under 6E, and this is what I get when I run it under 6D. You see we are missing, lexical actually missing one symbol, more than one. So when you work with pseudo modules and pseudo stashes, just remember that 6E is different. And the interesting thing here is that those are even different classes. So the pseudo stash in 6D and pseudo stash in 6E, they're different classes too, because they were too drastically changed to implement all the changes in one class. Okay, let's skip this one. And let's skip this one. I mean, those two examples I tried to show that my in-comp unit compare it to the global namespace. Sorry. Спасибо. Just as you can see, global in globalish doesn't have any symbols, but my has, because my treats comp unit a little bit differently. Let's not focus on it. Okay, yeah, just a few of other pseudo modules I haven't mentioned. Outer, dynamic, and there are some more. And here is documentation page which will provide you with all the pseudo modules available in Raku. Script. Okay. Containers. So before moving on to containers, let me just summarize a little bit what's been told. The whole section is dedicated to symbols and symbol tables. And basically, what I tried to show you is that Raku compiler operates with symbols in first place. So it doesn't work with values directly or whatever. Compiler knows about symbols. So what about values? And what exactly happens in this example? Yes, of course. Doesn't make sense here. So, as you can see, when I assign a new value to foo, it gets assigned. No problem. Bar is bound to value 13. And when I try to assign to bar, I get this kind of error. If we take this simple example, we declare a constant and also try to assign to it, we actually get the same error. And this one is clear. Okay. So, as I told you, compiler works with symbols. The semantics of this line, we take symbol bar and we bind it to number 13. So basically what we get here, we get a constant $bar. So it looks like a variable, it looks like a scalar, but in fact it is constant, it is immutable. And the similarity of the errors reported to us indicates this this situation clearly. And here is why. Let's consider a new introspection method, .var. We take these declarations here, one scalar, one bound symbol, an array, and a hash. And then we use .var on them and report its name. And also we report it without .var. This one. We got this kind of table. Scalar int, array, hash. So what is .var? The most simple explanation of .var method is it provides us, the method provides us with the object which is bound to our symbol. For bar here, I think it's pretty much clear. Bar gets bound to an integer number, and this is what we got in the first column. We got int as class name for this object. Then what is scalar in the first line? Okay. Scalar is very much special in Raku. It's a container class. It's a class, instances of which are responsible for storing values. What is the difference? As you see in this example, the difference is what is your symbol is bound to and how you access a value. So when we access a value which is bound to bar, we get directly to the number because it's binding operation used. But with foo, the sequence is a little bit different. The code generated for you by compiler first accesses the scalar object, and then it pulls the value 42 from an attribute of this object. But everything is done totally transparent 3. Okay. The cap signals, it's because I'm calling a meta method name. Because if we need to know the name of the class which is on the left hand side of this operator dot cap, then we ask meta model about the name. So basically the full this would be the full representation of this shorthand form. Oh, okay, I feel like I lost track a little bit, and I'm afraid it's not really clear. So back to the scalar. Again, as I told you, there is no easy way to get hold of the scalar object. Raku does everything to hide it from you. So, for example, what is this line here is about? Well, kind of a simple assignment, isn't it? But in fact, the sequence of actions taken here to implement this declaration is, first, a scalar instance is created for you. Second, that scalar instance is bound to the symbol $bar. And third, value 42 is put into that scalar instance. So remember that clickbaiting headline unused in the beginning. There is no variables in Raku. This is true because a variable in Raku is a compound thing which is represented by a symbol in a symbol table and by a scalar instance. And being put together, they create a variable, because as soon as we replace a segment here with binding, we get not a variable, but we get a constant. And same actually applies to some other kind of classes in Raku. As you may remember, when we were dumping symbols earlier, I mentioned that ampersand is the sigil of a subroutine. So a subroutine, from the point of view of Raku, when we make a call like this, it translates into find symbol ampersand foo, get a code object this symbol represent, and invoke this code object. So when you say that foo is a subroutine, actually, again, we deal with two entities. We deal with a symbol in the symbol table, and we deal with actual subroutine object, which is created somewhere. And because scalar is so much elusive, the only way we can find out about it directly is by revealing the symbol. What is our symbol in the symbol table is bound to using the bar method, as I already told you. So this example pretty much summarizes those details. So value, but it's scalar. Then we bind bar, and still we get value, but this time it's bound to integer. And then we rebind again, well, it's rebound. We got it. Yeah. Okay. At this point, the last thing I have to tell you about is that remember about the error in this example where bar is bound to 13 and we try to assign it, we get a failure. Because the assignment operator in Raku, it expects the thing on its left-hand side to be a container. And we have actually three kind of containers. Scalar, which I'm focused on right now, but array and hash are containers too. And it makes things like this possible. And 12 binds directly to it. Okay. So I have a feeling like I failed to be really clear here because subject is might be somewhat confusing initially. It may require some time to, get used to it, to grow upon it. But for now, if you have a question, anybody of you? Okay. Oh, it was a bit too fast. Okay, I hope so. So I already mentioned that the compiler deals with symbol tables. And here I'm going to do some little fun again, because it's getting boring. So a symbol can contain any symbols, actually. A symbol in the symbol table. Because it's a stash is hash, and hash does not provide any limitation on what kind of keys can be stored in it. So we can do many different things with them. Nothing really new here. Yeah, before having some fun, we have another subject. We have to better look into how symbols and containers are related. So if you take this example here, again, I declare a subroutine, and then I see what symbols are available to me. And I see that foo is here declared. It's no new to us. And then we use foo not as a subroutine to be called, but we use it as a symbol. And we introspect this symbol. And what we get an instance of sub with an ID. And then we refer to our local namespace and pull out the symbol out of it and introspect it. And of course, we get the same object. So these two lines simply show us how a symbol we refer to directly in syntax is related to a symbol stored in a symbol table. And then just different ways of using that symbol. We can just mention a name, and the compiler knows that if we use a bare word, that it's not a type object, not a constant, then it's likely to be a subroutine to be called. And so it calls it. But then we can be explicit and call it directly. And well, have the same effect. But then we can do it like this. We can pull a symbol from the symbol table and call it. And while this particular form itself is not very much useful, but when it comes to indirect invocation, we can use the symbol table this way. And so our code may not know what exactly is stored in this name. It just tries to pull out a subroutine and again call it. And there's 4 ways they're same. And why they're same is because whichever approach we use, we end up with a sub-instance. And actually, when we call this instance, we can use a dot. This is actually the full form of invocating a callable object. It's kind of, calling a method braces on our subroutine object. And also, this is pretty much clear because symbol is just bound to a container. When we pull out a symbol directly from the symbol table, we can use it as a container. We can assign to it, and it works. 42, 42. But we also can do pretty much illegal things. So don't mind the code below this selection. This selection is understandable. We create a subroutine, we introspect it, and then we call it. Okay, not before I explain later. But then we do something pretty much illegal. I create a variable, basically create a scalar. From now on, the word scalar would be more appropriate to the context. And I bind this scalar to ampersand full symbol. So I effectively override the symbol with different object. And then I introspect it, and I try to call it. And what I get, those 3 lines are coming from the start of the script. So we have a subroutine, and when we call it, we get some output. But after binding this symbol, subroutine symbol, to a scalar, this is what we get. We get a value 12, and we get it from here. And look, I reference it as a subroutine. And then it all ends up with an error. And the error comes from here. Because foo is not a subroutine anymore. Symbol &foo, which Raku compiler expects to be a callable, turns out to be a scalar, and the scalar cannot be invoked. And this is what the error message tells us. And I will get back to this error message later because it provides some useful information for us too. So what this example gives us? It gives us clarification of the fact that compiler, again, it doesn't care about what is symbol bound to when it interprets it. It just takes a symbol and tries to use it the way we ask it to. Because here, it's us who asks compiler to invoke this subroutine, even despite the fact that this symbol is not a subroutine anymore. And now, just some fun. And really, just don't tell anybody I saw you this example. It's terrible, but it really helps to understand how things are working in Raku. Our is another pseudo module, which represents public symbol table at the current scope. And then I create a symbol with this terrible name. And believe me, there is no syntactically clear way to reference this symbol other than use it as a key of a stash. And this is what I do in the second line. It's 42. So, as somebody mentioned, noticed this unit marker earlier. This symbol does exist in our namespace, but because it's a legal symbol, we cannot accidentally reference it from our code. And basically, it doesn't have any value assigned to it. It is used internally by the compiler for compiler needs. That's it. So the symbol exists, but it's useless for your code. But it's okay to have this symbol because really, again, symbol tables don't care about the exact symbols used in symbols. That's great. Exact characters used in symbols. Good. This is, in this example, with this example, I would try to show you another property of container, of scalar container. It actually can contain any value, any object, any type object. A scalar basically, in general, doesn't care what it holds, which means that a scalar can contain an array as well. And this is what we have here. And look at the output of the script. When we introspect foo, when we print it, we have the same result as when we print an array. But when we introspect what the symbol is bound to, we have a scalar. And in second case, here we have an array. But really, when we use those two symbols, there is no big difference which one we use in most of the cases. So if we need to reference an element from the array, we can do it like this. And here we get but there is a difference. Let me introduce you to one more introspection method, .Raku. The purpose of this method is to stringify your object in a way that it could be evaluated back into the same kind of object. So .Raku actually provides syntactically correct representation of the object that was applied to. And well, as far as I remember, yes, DD uses Raku. But the point is that DD simply dumps an object for you instantly. And for the purpose of my examples, I wanted to prefix the output with some meaningful information. So that's why I use .Raku. But yes, DD is the fast way to dump an object. That's correct. Good. Why Raku? What it gives us? Just one symbol, one additional character in front of the array we get, $sign. And it's actually syntactically correct construct. Say, you see, yes, it is accepted. What does it mean? What difference? The difference is this scalar. This situation when some kind of iterable object, iterable, I mean some kind of object which has many values and we can iterate over them. So when an iterable object is stored in a scalar, in Raku we call it itemization, because on certain occasions, which I'm going to tell you about, if an iterable object is itemized, it is considered as a single object, not as an iterable one. Okay, let's skip this one. In general, I hope it's clear to understand, and let's move on directly to why itemization is important. Okay, so again, we assign an array to a scalar. And here I'm going to demonstrate its so-called single argument rule. This is not something we have in Perl. This is something we haven't had in early versions of Perl 6. This principle which came later when a lot of problems was encountered with previous approach to iterable things. The single argument rule means that constructs like for do not iterate, they only take one single argument. And if this argument is not an iterable, then they don't go inside. They consider it as a single element. What it means in this example is here 4 takes an array. Array is an iterable. And foo is a scalar. And scalar is what 4 gets. And so it's going to be considered as a single. Which one? 8. You see, the first 4 iterated over an array. Each line is output of this statement. And second 4 over a scalar, we've got one single array here. Really, this is kind of problem people quite often come asking about. And many new guys stumble upon this principle because really, visually, well, as I shown you to you before, when you do say $4, you get an array. There is no visual distinction with say at A. So people expect them to behave the same, but they don't. They don't because of the itemization which taken place. Just let's make it more explicit. So in this case, it just explicitly itemized the array on purpose. And the outcome is the same. So before you, if you need to iterate over an array stored in a scalar, over an itemized array, you need to take some special methods, and we'll get back to it a little bit later. Maybe in this next example, let me check out. Yes. Why is this important, and what kind of problem did it solve? Let me modify the array a little bit. Look at this change. Again, yes, that's the thing which I forgot to tell you. So previously, this array would be flattened down, and the output would be 1, A, B, 2, 3, which is not always what you want things to be. If you need things to be this way, you have special measures to flatten down this array. But if you need to iterate over it as is, then itemization is the solution. The thing I haven't told you about is taking place implicitly. Raku itemizes this for you because by default, every elements of an array are itemized as scalars. Scalar. Scalar and scalar. The first one is just integer, and the second one is an array. But they are both itemized. Okay, how do we iterate over an itemized array when we need it? There are different ways. First one, the most straightforward one, is to turn it into array explicitly. We just prefix it with array symbol. Second way, we can turn it into a list. List is just one of the type objects in Raku. Basically, it's immutable kind of object. Oops, sorry. And the last one, we can simply strip out the container. This operator here, it is called decontainerization operator. And what it does, it throws away the scalar and returns the value the scalar contains. So what output we get? It's a straightforward approach, convert into a list, and decontainerization. And before we use decontainerization, as you can see, I'm trying to introspect it. So first, I tell you what's in the scalar foo, and then I try to introspect what the decontainerization operator returns to us. So first case gives us a scalar as expected, and second case gives us an array, just plain array. This approach is barely known by many raccoons, but it's very much effective. Okay, this script is somewhat complicated, but I tried to measure how fast each approach is. So I tried to measure how much time decontainerization takes comparing to converting into a list. And to using, and to provide you this clear example. Yeah. So decontainerization, converting into a list, and truly, I don't know why, but converting to the array is the slowest one. Probably, okay, I wouldn't be guessing why. But so, as you can see, the decontainerization operator is the fastest one. And for this reason, I pretty much recommend you this approach. Dot values could be, but dot values might turn to be even slower. So I can't tell you immediately, but I think it's going to be slower because still it would involve creating new objects under the hood. I don't remember what is the difference between small list and big list. The big list is a coercion method, one way or another. But what does the small list? I don't really remember for the moment. I need to refer. It's not that often as I use it. Good. Okay, a little bit late for this example. I have already told you that array by default itemizes its values. This example is about a little bit different thing. Why people are getting confused about the single argument rule when it comes to loops for in particular. Look, pretty simple situation. We create an array of numbers from 1 to 10. And then at some point in our code, we store another array into one of its elements. Sorry. And then we want to iterate over this element. And apparently what we get this array back as a single element. So 4 doesn't really iterate over it. You can agree that this kind of code is pretty much common everywhere, and therefore people quite often stumble upon this situation. So whenever you need to iterate, first make sure that you have something iterable. And this will spare you a couple of hours of debugging. Yeah, just another example of using the containerization for this purpose. Actually, besides of being pretty much performant, the decontainerization also convenient in a way that it lets us to, with decontainerization, we don't need to be worried about do we actually got an itemized thing or pure object, because if there is no container, the containerization will return you the object itself. Yep, you see. 13 here is a constant. And so when we decontainerize a constant, we get a constant back. So this is also one of the most safe approaches for cases when you know that we will definitely need to iterate over any iterable. Would it be containerized? Would it be itemized or not? Okay. Yes, you remember I mentioned to you earlier that list is immutable. Here is a plain list as we create it usually. So it's a list of elements. In this case, I wrap them into braces because otherwise Raku will try to interpret them as individual values, and will only assign one is a variable, here is a scalar. So with braces, I tell Raku that it's single list object. And I would like to be explicit about it. So then I introspect it just to make sure that we've got a list, and then I try to assign into the list. And Raku tells us that, oops, guys, it's immutable. You cannot modify it. So far, so good. But let's do things a little bit different. Let's include a scalar into the list. This is where the scalar is bound to. And we are assigned to this position. We are assigned pi constant. And that's what we get. We get pi in this position. So, does it break the principle of immutable list? Not really. What happens here is, again, a kind of symbol and object thing. Because we can consider a list as a table of indexed symbols. Here, symbol 0, symbol 1, and values are bound to those symbols. So at this point here, we take symbol 2 from a list and try to assign it into it. And this symbol is actually bound to a scalar. And the scalar itself is writable. It's mutable. And therefore we get no error. So we cannot pull out the scalar out of the list. Neither we can bind into it, because list is immutable. So when we attempt to bind into a list, we get an error. We cannot modify it, and bind operates directly on the list itself. But at this point, we operate on a scalar, which is stored in this list. And, well, I hope that this part is not going to be confusing to you anymore, because really, I had to push through this behavior for list and for map. Map is actually an immutable hash. And I had to do so to fix a problem with exporting symbols where map is used. And so we needed to decide that we need to break this previous behavior where list was implicitly decontainerizing things. You know, in early versions of Rakudo, at this point, the list would strip off the scalar of $foo, and it would store just plain 42. It's not anymore. So the list is really immutable, but you can store this immutable thing into the list, and you can change this thing. This is one of the principles which also might be confusing at the beginning, but when you get used to it, it's clear and pretty much understandable. And actually, if you need fully immutable thing, you can find among third-party modules implementations of tuples. Sorry, what was the second name? Sorry. Anyway, So tuple is different from the core list is exactly because it implicitly decontinuizes objects which it gets. So it's truly, kind of truly immutable, so on and so on. And I think at some point in the future, we're going to include tuples into the core of Raku, but it's not there yet. Oh, yes, this example is in here. It explains why we can assign PI into second position. So as you can see, first I introspect second index on the list, then I introspect $full, and it's the same scalar. Just consider the object ID. Okay. Okay. Anyone with any questions so far? Yes, based on this module. Yes. I mean, it's not a high priority task, so it's planned to be moved into the core. But since no, big demand on this, it's been postponed. Good. Just have a feeling that I'm missing something, but okay, let's move on. At this point, you might notice, if you didn't know this yet, that Raku is a language doesn't have references. It doesn't have any concept of references. And this raises a question. Since there are no references, arguments are always passed by value. How do we get writable arguments, modifiable arguments, and things like that? And the answer actually containers. And the way it works, it's still related to all this symbol object relations I was talking about lately. So let's take a very simple example with subroutine full, which takes an argument, which I'm gonna introspect. And remember, I was talking about NQP ops. I use NQP object ID here explicitly instead of using which. And I apologize for using this kind of low-level things here, which is really beyond the scope. But the problem about scalars is that which method on scalar reports the same object ID for in certain situations. So it's going to be two different scalar objects, but the object ID they report are going to be the same. So just this is the kind of issue I also stumbled upon recently and still trying to figure out whether this behavior is correct or not. So Object ID would tell us exactly the ID of the object that is like this. Okay, back to our example. We have two different calls to foo. We call it with a constant, and we call it with a scalar. But when we introspect the argument foo receives, it's always a scalar. One way or another, but we get a scalar. Each time it's a new one. So what happens here? Raku passes an integer object, but then it wraps it into a scalar and binds this scalar to the argument. Here, Raku takes a value from a scalar and wraps this value into a new scalar and binds it to A. Just so, as you can see, object ID for bar scalar and for the argument are different, which actually means that the value in bar from bar was re-encapsulated into a new container. Okay. What if we try to change the argument? We get an error. We get an error because because by default, Raku follows the principle of functional languages. Arguments are immutable. Unless we explicitly ask it to create a writable copy of the argument for us. And if we don't do so, we are immutable. Okay. But good. How much immutable is it? Well, basically the situation is the same as with the list. So if we take an array of some kind and supply it to a subroutine which takes a single argument, so we will get an itemized array, but elements of the array are still writable because what we are interested in is the array itself, the array object. And the array object is immutable, no problem here. And so, we've got an array in full, but the array is itemized. This is clear from this line. But then, no problem with assigning a value to 10th element. And we can compare it to bar, where we expect an array. Actually, to be correct, this construct, syntax construct tells us that we expect a positional. But for now, this is not important. And we also introspect the argument, and we are seeing the 11th element. And then we report 10th and 11th elements before and after the subroutine calls. Again, it's the same. So here is argument introspection from bar. Yes, we've got an array, but the thing is, it's also mutable array. So the two elements we modify, they were 10 and 11 before, and after calling those subroutines, we get strings in them. So basically, things are simple, but then we have two modifiers for the arguments. One is row and one is RW. Right. They are similar and they are different. They both allow us to modify a scalar. For example, let's tell the compiler that we want our argument to be a read-write one. Basically, from the point of view of the compiler, oh, I'm sorry, it's a bit. Yep, sorry, let's postpone. Right, I just missed one example. Let's start with isRow. IsRow means that we ask compiler to bind our argument symbol directly terminology. Again, terminology. Let me correct myself and change terminology. There is parameter and there is argument, and often they are interchangeable. I use the terminology in which, and basically Raku uses the same terminology, in which this is a parameter. So the symbol which we declare in subroutine signature, it's a parameter. And what we pass into a subroutine is an argument. So I would like to avoid this confusion, and I'm sorry for using wrong terminology. So back to isRow. Using isRow, we tell the compiler to bind our argument to the parameter symbol directly. This is why it's row. Let's see how it works. First, we take a scalar, we introspect it, and then we pass this scalar into full, and then we introspect it again. And you see, here in full, we try to assign into parameter. So I think the outcome is pretty much expected. The scalar, which is our argument, and this is the same scalar. Again, we call it argument. Okay, so parameter is the same scalar, as you can see. Then we assign 42, and when our subroutine is done, $v contains 42. So we operate, in this case, we operate on exactly the same scalar, and we can modify it. And this is how proper use of symbols and objects helps us avoid using references. So instead of passing a reference, we're still passing a value, but the value is a container. And this container has the value we are interested in. And we can modify this container. And all of this without any kind of references. And I think anybody of you who ever was writing in C knows how dangerous references are. So we just don't use them here. And I must admit that in Perl, passing values by references was also not my favorite kind of thing. It's not always easy to remember when you have to pass a reference, or when you can pass a value, or whatever. It's all pretty much confusing. In Raku, you just know that what you pass into method, into subroutine, whatever, is an object. It's always an object. And it's not passed as a copy. You just get the same object on input and same object on output, except for the cases when you don't care about the container and only about the value. Well, then you get this object just in a container. So the rest of the script, the end of the script, we try to pass a constant. And as you remember, our parameter is row, so it binds to this constant. And apparently when we try to assign into a constant. And of course, it's rows. So as you can see, when we introspect the parameter, we get a null, which is actually PI. And then it dies. So this is our one way to have writable parameters, but there is a better way. If you know that you need a writable, really writable parameter, it means you need a container. And when you tell the compiler that this parameter should be a read-write one, we tell the compiler that we expect a container here. The difference is how we get the error reported. Look, in the previous example, the error location is line 5. And yeah, we go to line 5 and well, it's pretty much innocent. Okay, here. It's pretty much innocent. Nothing wrong here, seemingly. But then we have to trace back and see that it was called on line 16, and there we might probably notice, might probably not. When we use RW, the error message changes, and it's more explicit about what kind of error happened. So it really tells us the expected writable container. And it also tells us, well, line 3. But line 3 is our subroutine signature. So it's easy to understand that something wrong about the argument. Then still we have to trace back to line 16 to see where it happened. But well, anyway, it's already much easier to spot the issue. Because, okay, this is rather simple subroutine. It's easy to see what and where and so on. But imagine that this subroutine calls a method, and the method calls some kind of callback, and the error happens in that callback. And tracing all this chain of events, it's going to be really some kind of pain in the neck. So we better cut off this kind of issue as early as possible. And EaseRW is one of the ways of doing it. And again, as you can see, it's all about working with symbols and objects separately. That's the whole topic I'm talking about for about, well, a very long time about. Right? Compiler always knows about symbols. And only when we ask it explicitly, like in this case, that we want something writable, it goes, it takes a special action and makes sure that the object we get is actually containing something writable. So the simple question then, why would we need row? Row is often used for low-level operations when we need to deal with type objects. So instead of saying foo of p, we can do it something like this. And then foo can operate on this type object it received if it needs to. And type object is passed as is without any containerization or any other expensive kind of operations. So this row has its own usage, but yeah, it has to be carefully considered. Just a little bit of syntax too. This is another kind of sigil in Raku, and this sigil allows us to create a sigil-less symbols. Oh, I'm sorry, I have to answer this call. Hello? Yes? Yes? Yeah, 1 second. Okay, my deepest apologies. Some kind of calls I simply have to answer. Okay, so back to I think. Could somebody please say something? I think my earbuds discharged. Hello? Yeah. One thing after another. Okay. Switch over to other ones. Okay, good. Back on track. Once again, I'm very much sorry about all this. So how much, whatever fun could it be, but really a SQL which allows to create a SQLess variable, that's our SQLess symbol. That's a little bit of a paradox, but still. Backslash actually equivalent to this notation. And in a way, it's all three are basically the same, except that here we have to use a sigil, and it's not always what we want. So just for you to know, there is no any specific in this. But most use backslash has actually in declaring subroutine parameters. Because when we see a parameter like this, we know that it's a row one. And so this notation will not confuse us. Though again, using of isRw declaration would be more correct because we do expect a container, but for an example, that's okay. That would be nice. So no surprises. We pass a scalar, it gets multiplied by 2, then we pass a constant, and we get an error. But this symbol has another use. And this time is also pretty much useful on certain occasions. We can create aliases. And in this example, as you can see, I create an anonymous class. It doesn't have a name, but I create an alias for it. And then I can use this alias for whatever purpose I consider necessary. So we can call a method on it. We can ask for class name, and we get this auto-generated name. And we can create an instance of the same class. And then again, the class name is pretty much weird because we haven't specified a name for it, so it was auto-generated by the compiler. But here in the code, we can use it named, and we know what it is. We can give it some meaningful name, because full, means nothing, but if we need it, we can give some meaningful name. So backslash as such is very useful symbol. time for advertisements. Have you run any advertisements already? Okay. When I get tired, I get too serious, unfortunately. Okay. We spoke so much about parameters here already and scalars, and apparently we missed the point about type checking. But because there is no really hidden things in type checking, I would like to mention just one detail. Another statement one can hear about Raku quite often is that Raku uses graceful type checking, and what people usually interpret it is that it's possible not to do any type checking at all. And similar to the clickbaiting headline, it's almost true, but it's not completely true. It's almost true, it's also almost false. Let me just show this to you and explain what exactly happens. So we have a variable, and apparently we can assign any value into it, any kind of value. It doesn't care. You see, no error, no output. That's just what. One step further, and we add another variable, and this time we would constrain it with to be integer. And let's introspect it. Okay, one more method, and this method of is a scalar method, and it tells us what type this scalar is constrained to. Let's go look. We have int and we have no. So int is expected, and no, well, it's something like we saw it before, but it's really something new to us, as a matter of fact. Well, at least in the context of this class, which is new. The next thing I do, I ask what parents our integer type has. And I ask for all parents, not just immediate ones, but I ask about all. And what it tells me is that it inherits from cool, it inherits from any, and it inherits from no. No is the root of all classes in Raku. It's, you know, it's like the ring to bind them all. Because whenever you create a class, as I told you, without any parent, it inherits from any, and any inherits from no. But we also have one specific data type called junction. And junction, as far as I remember, is the only type which inherits from no directly. All others are inheriting from any. So what is so special about no? Oh, no, not now. No accepts everything, literally everything. let me remind you about NQP and meta model. And for example, if you remember, when we asked about meta object of meta class, it told us that it's an object of it's an instance of NQP class how. What if you encounter this type object in Raku? How do you handle it? Because it belongs to completely different type system. Well, you handle it with mu. Even though mu does not inherit from NQP class how and NQP class how does not inherit from mu will match. And so if you create a subroutine, and then you do something like int. Oh yeah. What? NQP class how? Okay, again. Yeah, like this. And as I told him, NQP class how has nothing to do with mu whatsoever. If we try it like this, oh, it's even better. Ah, yeah. Okay, so I can't even ask it about its ancestors. It's in row because it doesn't have it. It's too low level, but still, well, I just know it's not there. And okay, let's have another fun. It was once asked long time ago, somebody asked if it's possible to create a class which wouldn't be inheriting from mu. And you know what? It's possible. Look, I have created a class which doesn't have parents whatsoever. It has a name, that's from another. So first two lines is what we're interested in. This class has a name, bool, like it's a scary one, but yes, of course I used meta model to create it. And if you want, you can have a look into the code, but I specifically made it one line so that it doesn't bother us with details. And again, I have a scalar, untyped scalar, which is actually typed as mu. And I can, here, I still can create an instance of this pretty much, strange class. And I can assign this instance to this scalar, no problem. Is my class a mu? No, it isn't. That's here. Just a little bit of black magic. So, once again, Raku allows you to do a lot of things, really a lot. Of course, doing the things comes at some price. So before doing some kind of black magic, always think twice whether you need it or not. And like in 99.99% of cases, really, you don't need it. But sometimes, really sometimes, knowing those steps are really helpful. Just one advice for those, when you do something like this in your code, do it neatly, wrap it, and document it. So outside, nobody must see it. You must well document some method, how it behaves, so that no surprises to people around. But just be careful. Any questions? Oh, yes, Daniel. Truly. Mu is not a kind of type which is often used in Raku. Most of the time, subroutines, methods, and other kind of code objects, they expect any. So be prepared that if you work with low-level types like meta model classes or some other direct children of Mu, expect that Raku would be exploding with type check errors. And a good note from Doombox. I just shown you that junction is the only class which inherits from Mu directly in Raku core. But the junction also has another specific in Raku. When you use it, it is possible that you have a junction with many values. Please go to the documentation and read about it, because I'm not going to tell you what junction is. It doesn't matter here. So it is possible that when you pass a junction into a subroutine, Raku will automatically split it in those values you have in it and call the subroutine in different threads in parallel to speed up things. It happens automatically and it's called auto-threading. Sometimes you may want to get a junction in this case, the only way to do so is to declare your argument as having type Mu. In this case, Raku will pass it as is, so you get bare junction without any, special processing on Raku side. Good. Last kind of container we have for today, and we're gonna have some fun when we're done with this container. Proxy. Anybody of you who works with JavaScript is familiar with proxy in JavaScript. It is basically the same in Raku. The purpose of proxy container is to intercept store fetch operations and invoke your code when they occurs. Yeah, it might result in side effects. So first, let's consider, as usual, let's consider some basic code. Here, first of all, notice that I use binding here. To avoid long explanations, just keep in mind that because proxy is a container, you cannot simply assign it into a scalar. You better bind it to a symbol. Very modern JavaScript, yes, very modern. I'm trying to avoid any old versions of JavaScript when I work with it. So when we create a proxy instance, we feed it with two named arguments: fetch, which has a callback for fetch operation, and store, which has a callback for store operation. Simple. A little bit of syntax here. This is so-called pointy block. It's another kind of, it's something in between a block and a subroutine. It is anonymous, but it doesn't have a name, but it has arguments. And the single dollar here is actually tells us that we do expect an argument here, but we don't need it. So we just say that, yes, we know there's gonna be a parameter, an argument passed, but just ignore it. We don't need it. We can do it like this, because actually this code is going to be invoked as a method, and we're gonna have a proxy instance in this argument. It's irrelevant. And then what we do, we just try to read from proxy here and here, and then we assign to it, and then we read again, and then we just try to introspect it. And this is very simple proxy object, which just increases counter on each fetch operation and changes it when something is stored. Well, this is not fun yet. This is rather boring, but we'll come to it. So as you can see, we had two reads. They correspond to those two lines. Then we have one store, this one here, and one more read. So the counter is now 11 because we previously put 10 in it. And introspection of proxy gives us a parameter proxy. Simple. But anybody noticed how I do it? I do assignment to another scalar, and then I do say on it. Here is the reason why. I told you that proxy can result in unexpected side effects. You see. Here we go. So let's talk about the side effects. Say. I use just say on this proxy. Kaboom! This is our first say. And instead of getting 1, it's the same proxy actually, it's just a counter. So, and instead of getting 1, we get 7. We do second call, and we get 7 more, we got 14. So, what's going on here? Accidentally, when people go this way, they reveal the way we they reveal the way Raku handles calling code objects and the way how Raku handles arguments. So what happens here? To make things a little bit more understandable, I have declared this foo subroutine, and it roughly resembles what say does. So it takes a raw argument parameter. I'm still messing up. It invokes method gets on it, and then it sends the standard output. And as you can see, it gives us 7 more fetch calls. Step by step. First, when Raku encounters a call to a multi-dispatch subroutine, 1 second. I hope everybody knows what is multi-dispatch subroutine. If somebody doesn't, please tell me. Okay, I think everybody does. So the first thing, Rakuda need to check if the argument matches the subroutine signature. And normally, sorry, slow. So normally this is the way how we declare a multi-dispatch subroutine. First, we declare a prototype. If we don't declare it, Raku does it for us implicitly. It creates a default prototype. So one way or another, it has to match if the argument can be accepted by this signature. So what it does, it takes a value from proxy. First, fetch. Then, yes, it does match. But we have a multi-dispatch. So we need to find a candidate. And for this purpose, compiler fetches a value from proxy again, because now it needs to match this value against signatures of possible candidates. And we have one more fetch. And then it does some internal processing of this value. And because we have row, actually row here as well, each time the compiler deals with the container itself. It deals with the proxy instance. And so each time it needs a value, it pulls it from the proxy, causing another call to the fetch method of the proxy. And so eventually, when it comes to this point, when it finds multi-candidate, the proper candidate, and it knows for sure that, well, it's time to call this candidate, it fetches the value again. But see, the candidate is a row. And so we fetch a value to get the stringification of it one last time. And here, this is why we get all those fetches. Multi-dispatch, signature matching, calling method gist on it, and a lot of stuff which happens behind the curtain, which we don't know about unless we go deep into the Rakuda things. So when you use a proxy, be careful. Be careful because it might be pretty much painful. Look what happens if I add 2 more candidates. You see, the list of fetches doesn't even fit into one screen. 14, 42, how much does it make? 32, 28 calls to the fetch method. So when somebody tells you proxy is slow, now you know why it is slow in certain conditions. But it's really useful in other conditions. It's really, I mean, don't avoid it, use it, but use carefully and wisely. Yeah, that's what I told you about. I promised you some fun. Oops. So let's have some fun. Again, we're talking about symbols, we're talking about objects, we're talking about containers. Let's create, excuse me. Look at this line here. One way, I create a variable which has a callable sigle, but I bind it to a proxy. And in this proxy, well, it's pretty much simple. I get a random value, and if it matches the conditions, it fires, and if it doesn't match the condition, then it misfires, so we just have a click. But we cannot store into it, so we just type. And then we call it. We call it as we would do with a normal subroutine. Russian roulette, as they call it. Once again, roulette here, it's not a subroutine, it's not a code object. It's a symbol. It's a symbol which is sigled with callables as a callable one. So what happens technically in this case? Again, Raku the compiler installs code which looks up, this symbol in this symbol table. Then it takes the object bound to the symbol, which turns out to be a proxy. Compiler tries to get a value out of this object as it would do normally. And in this case, proxy steps in. It intercepts this fetch operation, and it invokes our callback, which decides which of those two subroutines we must call. That's it. I think one thing I wanted to mention, I mentioned a while ago, but forgot about it, is that actually Raku is very consistent. Remember the case with hashes, where they inherit from hashes and behave exactly as hashes? So you work with them, like you don't care whether it's a stash or a hash. This is an example of Raku consistency. And here we have just another example of Raku consistency. I mean, a thing which is expected to behave as a callable do behave as a callable, no matter what's behind it. There was, yeah, question. There was different, very different options to implement. So, well, I could have launched a run -ref for that matter as well. So why not? And wipe everything out. Probably last thing I have to touch here is, after all, if we work, if the compiler works with symbols in the first place, why do we need symbols or sigils? Sorry, pronunciation. So why do we need them? Well, they provide us with meaningful defaults. Remember the example where I was introspecting different symbols and I was declaring them using different sigils, like this one. So apparently we get an array, a hash, a scalar, that's it. What if we don't have sigils? Wow, really? Just compare. Why do I have to type all this? And moreover, actually, when, as I told you about parameters, this sigil stands not for array. It's just the default that the compiler uses to initialize this container. But this sigil stands for a positional, which is more basic thing. And we can actually do something like this. And we get a list instead. Well, of course, we can bind this list to a scalar, no problem. And then we get an itemized list. But what if we don't need an itemized list? So, I mean, there are variants. So sigils provide us with meaningful defaults, which simplifies our life. One thing. Another thing, when we use framing code, then we make code more readable. Because really, when I see somewhere in the middle of nowhere, I don't have to, crawl across the code, find where the symbol is declared, find out what type it has, what form. I know it's a positional. It should be a positional. Well, as I showed you before, it's possible to change it and do some kind of trick, but we better not. This is not recommended. So most of the cases, if you see this symbol, you know it's positional. If you see this symbol, you know it's going to be hash or something hash-like, because again, this sigil actually stands for an associative, which is also more basic kind of thing. And because of those defaults, you also don't have to specify parameter types too often. So in this case, the subroutine expects a positional, and if we try, we get an error. Pretty much expected error because this is a string. It's nowhere close to positional. Well, this is one more way to introspect. Here we just take our subroutine symbol and take its signature object. Also note that how much everything is an object in Raku. Signature is an object too. It's a property of subroutine. And parameters of the signature are also objects. And so we can iterate over them and find out all the necessary information. Like in this example, you see, we ask for the first parameter and we ask what type it has. And it tells that it's a positional. Simple. Good. Any questions? Okay, and if no more questions, I have a question then. We are pretty much beyond 4 hours limit, and well, I have considering how much time did it take us to get as far, I probably need another hour or maybe a little bit more to complete everything, all the subjects I prepared for today. But Do you want me to continue, or is it too late already? Because I know in Europe it's, yeah, 10 past 11, that's quite a time. So what would be your opinion? Shall I proceed or shall we call it a day? Okay. Okay. Just give me a second. Good. The reason why I decided to ask you at this point is because, as you can see, we're gonna switch over to a completely different subject here. Everything I told you before, it was mostly user point of view, let's put it this way. So it's things which you're gonna use in your everyday programming in Raku. Here we will switch more into internals of Raku the compiler and see how things works internally. And this is really interesting. Actually, when I started with Raku, it was still Pro 6 back then. One of the first things I stumbled upon is that with Mu, I got used to lazy attributes. Okay, let me finish. As you maybe know, Raku doesn't have lazy attributes as such. And I was missing them pretty much, so, well, I decided why not to implement them. And alongside with laziness, also some other functionality which is not present or was not present in Pro 6 back then, because some of it has been recently done. And so I started writing my own version of attributes and found myself crawling a lot in Raku sources and finding things which were simply amazing for a newbie. And that's how my path into Raku development started. So now I have two things. I have EtherX Muish module, and I have a membership in Raku core team. Both came as a result of this simple wish, simple desire. So, as I told you before, I hope that at some point you're gonna be interested in participating in Raku development as well, and I hope that your path into this direction will start somewhere around here. Well, I can continue today if you want. I can continue. It's I'm not that much tired, and maybe our European participants would vote for another day. So what would you say? Okay. Okay. I have water. I have a little bit of coffee. So let the marathon begin. Well, continue. Remember I told you that the three components of Raku compiler. The compiler itself, the compiler as an object which is responsible for syntax and for code generation, meta model, and the core, how they interact with each other, that they're tightly bound together. This is what I'm going to talk about right now. Very simple example. Again, I promised not to talk about syntax, but again, we're talking about syntax. Of course, what we get here, we get 3. Actually, we can do it other way around. We can do it like this. And we get the same outcome. Why? Because technically what happens here, when the compiler encounters an operator, it looks up for a symbol which starts with this prefix. Depending on what kind of operator is it, of course, because plus is infix, we also have prefix, we have circumfix, and we have post-circumfix. So in this case, we have an infix operator, and so the rest of the symbol must have this look. And so Raku does not sum for us. What it does, it calls a subroutine infix colon plus. That's it. And this subroutine, it's here, and it is one of the core symbols defined for us. And what it actually means, let me see, no, I don't have it. It means that because it's a symbol, we can change it. What am I missing here? Okay, sorry, I came unprepared for this one. Where is it? Here. Look, I added those exclamation marks, know precisely that it was our subroutine call, not anything else. And look that as a result of this call, of course, this is a bad place to do. It's clear. Here. Because it must look as an operator, but you see, the outcome is totally the same. So what exactly happens here is that the compiler installs a lookup for this routine infix plus. And because the core setting is our lexical outer, we can override lexicals, and we do override this routine. And instead of calling the core version of this routine, the code calls our own version. This is how you can redefine operators in Raku. Just brief insight. As a matter of fact, in real life, we usually need to declare it as multi because the original infix plus is multi, and we have to type those parameters because we don't want to catch up with every parameter. But again, it's another subject. That's too much. And I would like to proceed further and talk about less apparent things. What happens here in this example? You all know that eval is a very dangerous operation which caused a lot of headaches to security engineers across the world. Sometimes consequences of using this function was really dramatic and disastrous. So Raku takes care about this, and whenever it sees eval applied to scalar, it issues an error because eval is a very dangerous function. But we do need it. We know exactly we need it. For example, eval is used extensively in test module purpose. So to let the compiler know that we do it intentionally, don't be worried about it, we use this program, monkey see no eval. It's a kind of fun Larry likes, as far as I understand. I think it was his idea to call it this way. So, and as you can see, it was eval successfully. We got output of the code we have in this string. What exactly happens here is when the compiler crawls over the lines of our code, it encounters this program and it raises a flag that, well, okay, if you see an eval with a variable, don't worry about it. That's okay. There is another way to do it. It also can call a subroutine with the same name. And if the subroutine returns true, it's also a signal for the compiler that it's okay to have this eval. So what we can do, we can intercept this kind of call and do whatever we need. For example, we might try to determine whether this eval is legitimate or not based on some conditions, or maybe we can turn it on or off dynamically depending on what kind of environment we are running in. It depends. We can do whatever we want. But the point I'm having here is that you see this subroutine is never invoked explicitly, but it's been invoked by the compiler. And when this subroutine is invoked, it also poses some interest, but we get to it somewhat later. I have a note that we might possibly consider. Oh yes, that's another fun example. Remember I told you that if you create a symbol on process namespace, you get a dynamic variable. Well, there is another way. Actually, when the compiler encounters a reference to a dynamic variable, it doesn't resolve it directly, but instead it finds a subroutine named dynamic, and apparently it works with symbols, so it looks for symbol ampersand dynamic, and then when it finds it, it invokes this subroutine with variable in question, variable name in question. Here we go. This is the output we've got from our subroutine. And then you see I redirect the call to the original subroutine. It's also possible because of another pseudo module named core, which has all the symbols defined in core. Sorry, what do you mean levels of danger? Okay. Yes. Okay, this we spoke about. Yes, because compiler needs to deal with the type system. It also relies on metamodel to know how the type system works. Sorry, William, because I started another subject, I still don't get what you mean. So when, please ask me again a little bit later when I'll be over with this subject. Yeah, so back on track. So it relies on metamodel, how to handle type system. About the core setting to provide static symbols, I also just shown you because this is an example. Dynamic is defined in the core and the infix plus also defined in the core. So this subject is covered. With regard to metamodel, we need to get a little bit later to it maybe. Yes, we will. And yes, I also just shown you how some core routines involved directly. Dynamic is one of the core routines which are involved, straight away. So it's time to move on and see what happens when we declare a class. Because this is the point where metamodel gets extensively involved. As I showed you before, classes are backed by class how metamodel classes, metamodel class. What happens internally? How exactly a new class gets declared? So in this example, I will try to roughly reproduce all the steps compiler takes to declare a class. First of all, compiler doesn't know about classes. Really, it doesn't. It knows about the keyword class. And it approximately knows that it's kind of a package thing. I mean, class is a kind of package, not exactly as it in Perl. Well, that's a different story, but, well, in some way. So compiler has to find out how to create a class. And the first thing it does, it takes a namespace called expert how. Oops, I always expert how, and it takes a symbol named class defined in this namespace. And this symbol is expected to be bound to the meta model class, which would implement the class functionality for us. So let's have a look what we get from there. Okay, pretty much expected. We get meta model class how. Okay, let me skip this one for now. It's not really relevant. Next step the compiler does, it takes the meta model class it found and it explicitly asks it to create a new type and gives this type name foo. This is where we get, once again, this is where we get a type object for our class. Once again, type object. I mean, the concept of type in Rakuda is pretty much extensive. We have classes, we have enumerations, we have packages, modules. They are all type objects. And classes is just one of the type objects, one of many. So new type creates a new class for us. I wouldn't be showing you the code of new type method, but you can find it yourself. Just grab over Rakuda sources and look at class how. But internally what happens is first a new instance of class how is created. And then method new type is called on the instance of class how. And what we get as a result, we get a class type object, and we get a meta model object which is bound to it. So for each individual class, we always get one individual meta model object responsible for it. And this is the one we get with .how method as I showed you earlier. Next thing, we need to add a method to our new class. So for simplicity of introspecting things, I just assign it to a symbol here, because I would like to output some information about it. Then let's say that the class declaration is done like this: class foo does R, which means that we want a class foo which would implement role R for this purpose. This is how we do it in meta model. And this is the code which actually does compiler when it adds a new role to your class. Then we actually add a new method and we specify which method name do we want. You see, the point here is this is the name which is going to be used to install the method as a symbol into our class. And this is the name which will be assigned to the method object. Well, if it's not clear to you what happens, you can simply change this string here, or you can change method name and then try invoking different kind of methods on this newly created class and see what happens. And you can also introspect the method and see what it reports to you. It's going to be also some kind of fun, but eventually you'll get used to it. And the final thing, our class has to be finalized. And this is what we do with method compose. So in the end, we have a fully fledged class. We can work with it. Here is the method we're going to install. Here we just reported our class. So we have class foo, fresh and new, shiny class. Then we can call method foo on it. Yeah, first we instantiate the class, and then we create it, and then we call method foo. And then we call method bar, which is actually declared by the role we consumed. And it also works. Whoops, we just created a new class manually. Everything is possible. So what's the point of this example is I wanted to show you the way compiler interacts with the meta model. And because I tried to reproduce what compiler does, well, it's a way to show you how compiler uses our meta model in first place. And so on, and profit. Yes, we got a class. And you know what? I have a bad feeling that my throat is probably getting really bad. Just, you know, unexpectedly a little bit. So I probably would stick to the proposal to split this talk and to finish it on the last day when I get better. So if you have any questions, I would gladly answer them now. So, but otherwise, I think I'm sorry, but we would better finish for today because tomorrow I have another talk and I better be able to have it. Yeah, it was a pleasure. Yeah, thank you everybody. It's really great. By the way, the question about monkey sees no eval and eval. Method form of eval is a function form. Okay. Okay, so probably it's clear now. Fine. So thank you everybody. It was really a pleasure and see you tomorrow. See you at the conference and specifically at my tomorrow's talk about my test async module. And also Sunday, I hope to have this all finished because what I have not told about is how objects get constructed, because it's also a subject which is not only useful for developing Raku, doesn't matter, but also it's great for a user because when you know how an object is created, you can do a lot of things with it. So I hope to cover this on Sunday. Will it be possible, Andrew?
Yeah, I think so. I think we can just cancel the replay of Daniel's talk because it's already recorded and we can just allow people to watch it on YouTube. And then I will put you in the schedule as the last talk on the last day, if that suits you.
Mm-hmm. That's good. Okay, once again, thank you everybody. It's really a pleasure.
Thanks a lot. It was really almost a marathon. But yeah, so we continue tomorrow at 3 o'clock UTC, and yeah, we'll see how it goes tomorrow. So see you later. Thanks a lot for everyone and for the for the speakers of today.